curiosity in motion. The next era begins with you, innovating, exploring, going further. From clean energy to quantum breakthroughs, we're shaping what comes next. Over the next 8 days, FabX comes to life. 42 speakers, 255 sessions, 100 chances to get hands-on, 5 evenings of conversations that matter, and 6 mobile Fab Labs, arriving ready to build, share, and inspire. From every corner of the world, you're coming to be part of it. This isn't just an event. It's a celebration of making, sharing, and shaping what comes next.
Good morning, everyone. Hi. And welcome to day 6 of FAB25 Czechia. And first of all, guys in the front rows, watch your legs, because this whole thing is about to start spinning now. Welcome to day 6 of FAB25 Czechia, and welcome to Prague. For those who didn't meet me back in Brno, I'm Sonia. And just like many of you, I'm a maker. A very proud member of Maker Movement, and I lead a marketing team at FAB Brno. And as for today, I am honored to be your host. Before we jump into what's coming next, let's take a look back at how you enjoyed our Maker Train workshop. Let's roll the clip. Yeah, thank you, guys. You deserve this round of applause for sure. Yesterday, we collected a few hundreds of those, and now we are going to take them to the post office and send them to your home countries and hometowns. So thank you very much for being so creative with us. I think it's safe to say that Brno gave us a very strong start. So let's keep the momentum going, right? Now, it's time to show some love to people who make this event possible. FAB25 is hosted by 5 organizations. Make More, Fab Lab Brno, Czech Association of Open Workshops, the FAB Foundation, and the Center for Bits and Atoms at MIT. We're also supported by major local stakeholders: City of Brno, South Moravian Region, JIC Innovation Agency, Kunst Creative Hub, National Theatre Brno, and also Prague City Hall, Prague Exhibition Grounds, the European Union, and Ministry of Education, Youth and Sport. And we owe a huge big up to our amazing partners, because without their support, we simply wouldn't be able to organize event of this scale. So our general partner is Prusa Research, and these are other partners of FAB25. xTool, Chevron, Dassault System and SolidWorks, the Fab City Foundation, Škoda Auto, the Innovation Center of the Ústí nad Labem region, Masaryk University in Brno, Brno University of Technology, ESA BIC Czech Republic, and our technological partners are Mechanika, Trotex and Megaflex, media partners Hexter.io and Make, and to point one of our community partners, Prague City Tourism, helping you to explore Prague easily. Speaking of Prague, we are in a new city, so let's get you up to speed with some essential info to help you navigate FAB25 in Prague. We are now in a Prague exhibition grounds, a legendary venue that hosted countless events, including Maker Faire Prague a few weeks ago. For FAB25, we transformed this theater, also taken over 3 pavilions, and added a few extra touches to create our very own FAB25 campus. This will be our base for the next 3 days, so make yourselves at home. This theater is something truly special, as you've probably already noticed. From the biggest stage in Central Europe, we've stepped into a 360 degrees auditorium with rotating stage that not only spins, but it can also move up and down. One-of-a-kind venue for a one-of-a-kind event. But now, let's walk you through the different pavilions and what's happening in each of them. Pavilion E. This is where the most of the workshops will take place. You will also find there several partner setups inside, so go and say hi. Pavilion D, packed with hands-on workshops, a laser zone, 3D printing farm, and some very cool partner activations. Definitely a space to explore and create. Pavilion C, here you will find the Prusa zone, the Art and Design Expo, and the stage where more talks and panels will happen over the next few days. And then there is a Mobile Fab Lab zone. Visit the unique gathering of Mobile Fab Labs and talk to the people running them. And if you need a break, head to our chill out zone, grab a bite in the food zone, or swing by the info point if you need any help. All of these are located outside. Guys, make the most of it and enjoy exploring every little corner of FAB25 campus here in Prague. More practicals now. We are sticking to our one and only rule. No food and no drinks in the auditorium. And also, please leave your bags and laptops at the cloakroom. Thank you in advance. You can connect to FAB25 network in most part of the campus. And please continue using the official FAB25 app. It's called Avanti, and it has proven to work really, really well. So you can build your own schedule, you can make connections, get live updates, and also ask questions to our speaker for selected sessions. And today's program track is called Emerging Technology. Together, we will explore 2 forward-looking themes, quantum in Fab Labs and open engineering. Let's start with quantum. Yes, we know it sounds like something from a physics lab or a sci-fi movie, but what if quantum technologies didn't have to feel so distant, abstract, out of reach? How can Fab Labs make quantum more understandable, tangible, and closer to everyone? Today, we'll start with an introduction to the topic from Neil, followed by several projects and initiatives from the world of quantum. Next, we'll turn to open engineering, a theme already shaping the way how we design, share, and innovate. This approach is rooted in open source values. It's all about building things openly, working together, solving problems as a community. In the second block of talks, after the break, we'll hear from developers working on open source hardware and software from all around the world. All this because we believe that emerging technology don't belong only to big tech, clean labs, and corporations. They belong to communities that are ready to explore, test, and push boundaries further. And just like every FAB25 track, we'll leave you with one simple question to carry with you through the day. And here's today's one. How can Fab Labs adopt emerging technologies quickly enough to stay at the forefront? Remember, there is no single right answer. It's just something you can reflect on by yourself, share it, or discuss it with your friends and colleagues over a coffee, whatever you want. And now let's start with the talks. In the first one, we'll hear from someone who knows what it takes to bring bold ideas to life and into global markets. With over 15 years of experience in leading marketing and PR roles across international companies, she has built a strong track record in brand development, global expansion, and high-impact campaigns across diverse markets. Today, she leads the European and UK presence of xTool, helping bridge creativity and capability one spark at a time. And just a quick note, please make sure to visit the xTool in our partner zone in Pavilion D to explore their machines. You can see them in action and even give them a try. And now, please welcome to the stage Salomé Bibilashvili. Welcome.
Thank you, Sonia, so much for the warm introduction. And it's really, truly my pleasure to speak to the community that truly matters to xTool. Okay, before I dive into my presentation, let's have some fun memory together. May I ask you to put your hands up in the air? Okay, thank you. So, during my speech here, my colleague in the backstage will try to engrave the AI sketch photograph that I just made on a wooden plate, and one of you will take this back home. And that's not just all. This one lucky person will get a very good surprise at the end of the presentation. All right, so at xTool, we are truly happy to support the FAB25, not just as a sponsor, but as a believer in people, in education, and empowering the accessible tools. The theme of the event would not align more on what we stand for, bridging the gaps. We see the transition in the world from a technology to education, from curiosity to real capabilities, and from the ideas to making them real. And this is how we try to bridge the gaps, because we identify the certain gaps in the industry, that they truly exist. We talk every day to the educators, to the makers, to the students, and those gaps are really real. One teacher approached us saying that he would love to have the hands-on experience in his classroom, but those tools are sometimes too complex to be used, and he was not a very tech-savvy person. Or the students just some weeks ago came to our booth saying that he's all about the creativity, but he does not know from where to start. So we encountered three major problems. Technical, some of the tools are too complex to be used. Educational, not all the curriculums translate into the real-life skills. And resource-based, not all the labs or educational organizations can really have the affordability to have the maker spaces in their facilities. Therefore, we came up with three major solutions. The first, simplicity by design. All we do is really about a drag and drop, plug and play that is truly easy even for a child to use it in everyday life, and they already do. The second one, education meets creation. So we will launch the xTool EduKits that puts together the ready lesson plans, teacher trainings, and our tools that really turns the classrooms into the workshops and turns the students into the makers. And the last one, Fab in a Box, and that one is really, truly a game changer. So we've combined together the tools, the content, and the support that enables the labs and educational organization with very affordable prices to have the maker spaces in your facilities. And we truly are very proud to support them already from Europe to Asia. So let me give you a quick glimpse how we bridge the gaps in around the world. All right. So later today, we will having a workshop in a D pavilion, and we will try to give the new life to the Orlo's very famous astronomical clock. That will be the hands-on work, hands-on experience. So I would love to invite you all at our workshop. And then, if you are an educator wondering how to engage more your classroom into the learning process, or if you are a maker thinking how to do more with less, or a lab leader to figure out like what to do more for your community, we are here to bridge the gap and to be your creator co-partner. All right, so before I was doing my best on this stage, my colleague has already engraved our photograph. Oops, sorry. And that's the surprise. Whoever catches this will take back home our F1 laser engraver as a gift. Ready? I'll try my best to be not biased. Okay. Please find me somewhere else so I can give you the details. And thank you so much. All right, that was it. Thank you.
Thank you. That was so cool, interactive, and congratulations to the lucky winner. Okay, moving on. Today's keynote comes from someone who truly needs no further introduction. He will kick things off by setting the stage for both of today's main topic, quantum and open engineering. So please give a warm round of applause to Neil Gershenfeld. Clicker. Okay, we need a clicker, guys. I don't know where to look. Good morning, Neil.
Good morning.
Yeah, we have a clicker. Okay. Thank you. Here you go.
Great. So let me start by thanking the organizers for, I think, the best organized and run FAB event ever. All of you. And as a vignette, this is the International Year of Quantum. Oh, and let's see, there's my clock. When they approached me about speakers, I suggested, rather than just a speaker, we should have a quantum day. And they kind of gasped. And what does quantum have to do with Fab Labs? And that's what we filled in. So think of this talk as an overture for the day to come. And like a good overture, it's going to be somewhat ominous and scary, but lead into the opera to come of the quantum day. So this is the International Year of Quantum. And what does that have to do with Fab Labs? So in the next 20 minutes, I teach at MIT a class called The Physics of Information Technology, where I answer questions like, why does it take energy to think? Or how do you make a teleporter? Or how do you make an invisibility cloak? And I'm going to try to do in 20 minutes the quantum part of the class. So let me start with a machine that looks like it would fit in a Fab Lab, almost, but there's two differences. One is this machine comes from the 1800s, not the 1900s, the 1800s. And the second is this machine is way beyond any tool you have. It's a reciprocating machine, and each pass-through moves by the wavelength of light. It makes a diffraction grating. It's much, much higher resolution than anything you have. It draws lines at the wavelength of light. That was used, and one of my projects I'm dying to do is I want to make one of these. I want to catch up to the 1800s in our Fab Labs today. That makes it, and anybody who wants to work on it, come find me. It makes a diffraction grating. Fraunhofer in the 1800s used it to look at the solar spectrum and saw, rather than being continuous, there were discrete lines. Those lines then required the invention of quantum mechanics to explain them. So, who's heard of SI 2019? Maybe one person here. And he doesn't count, you'll see why. This is the strangest, most amazing, most bizarre tech thing to happen in your lifetime, and you've probably never heard of it. So you use units, volts, amps, current. they trace back to standards, and there was this really bizarre one. The kilogram was a lump of metal in Paris, and Czechia, US each had their lump of metal for the kilogram, and they disagreed. We actually didn't know what the kilogram weighed because the national kilograms weighed different amounts. It was really embarrassing at the root of metrology. So in 2019, the kilogram was abolished and it was replaced with quantum mechanics. So in the upper left are 7 numbers. The last one is sort of weird and we don't like that one, but 6 good ones. Those numbers aren't measurements, they're definitions. Those defined quantum properties: hyperfine transition, speed of light, Planck constant, elementary charge, Boltzmann constant, Avogadro constant. Quantum properties. In terms of those 6 quantum properties, we define time, distance, voltage, current, all derived from those quantum properties. At the heart of it is this thing, the Kibble balance, which my colleague you'll hear from actually worked with Kibble. He'll tell you about this. This is the quantum kilogram. It's an incredible apparatus. It's run by a colleague I have at NIST, National Institute of Standards in the US. The way you measure a kilogram is you use the fractional quantum Hall effect to define resistance, and then you use superconducting Josephson junctions to define voltage. And then with current and voltage, you don't measure them at the same time because there'd be dissipation, but you make a voltage measurement and then a current measurement against a force, and then that defines a kilogram. And so to weigh something, the traceability requires quantum phenomena in the Kibble balance. And I'm showing here, this doesn't have the quantum part, but my NIST colleagues developed a Lego version if you want to make a Kibble balance in your lab to show the principle of how that works. So now continuing on into scarier parts, all of these images come from this book from this class. And so here I'm showing the problem set where you analyze the Kibble balance. And now let's get to the heart of quantum mechanics. So a quantum system for today's talks has 3 properties we care about. The first one is superposition. And so if you have 2 quantum bits, instead of being like 0, 1, they can be in 4 states, 0, 0, 0, 1, 1, 0, 1, 1. And they can be in all of them at the same time. And they can have a different probability for each part. So that's called superposition. But that's familiar. Classical waves superpose. You can take red light and blue light and have light that simultaneously has a mix of red and blue. So that's actually familiar. The second property is no clone. You can't copy a quantum system. And that's a very fundamental property. And then the third one is the really bizarre one. This is the really important one. It's entanglement. So what I'm showing in the right is if you have a decay process that emits 2 particles and there's no net angular momentum, you have to conserve it. And so they end up in what's called a singlet state, which is down, up, minus up, down. And so that's their state. If you make a measurement of which way a particle is pointing, it has to decide to be down or up. So you don't know if it's going to be down or up. It could be random chance. But when you measure one particle and you get an answer, the other particle has to be in the opposite direction. But now here's the really, really bizarre thing. If these 2 particles decay and one is on Earth and one is on the moon, when you measure the one on Earth, you instantaneously know the orientation of the one on the moon. It's not a telephone. You can't send a message that way. But what you did on Earth has changed what happened on the moon. This just is bizarre. So there are many explanations for it. Like, one is there's hidden variables, but we know that experimentally isn't true. One is information is going backwards in time to the common origin and then forward out. Murray Gell-Mann, a Nobel Prize winner and physicist, almost literally rapped me on the knuckles to say, don't try to explain it. Your brain doesn't go there. Our brains come from the world of this stuff, and the problem isn't interpreting it, it's the attempt to interpret it, just shut up and do the math. Any way you look at it, this is just bizarre. There's this weird non-locality. This is why Einstein didn't like quantum mechanics, but it's enormously experimentally validated. So the heart of quantum systems is entanglement, is superposition, that's straightforward, but also entanglement, and that's not. So a colleague at IBM invented quantum cryptography, and so that's based on the no clone. So if I send you a message, historically cryptographers talk about Eve as the eavesdropper. Eve could listen in on the message, and if I send a bunch of photons in a fiber, she could take a few and I wouldn't even notice that. But you can generate single photons and you can detect single photons. So Charles realized that if you send single photons and you pick polarizations, if the eavesdropper measures the photon and they don't match your polarization, they'll mess up the photon and you can detect they messed with your photon. So based on the physics, there's no way to eavesdrop because of quantum no clone. You can't copy a quantum system. So the no clone lets you do completely secure quantum cryptography. It's a fair amount of work, so this isn't used for routine messages, but this is now deployed for quantum key distribution for conventional crypto systems. And this has been done up to satellites in space. It's been done over many kilometers and fibers, sending one photon at a time with very sensitive emitters and detectors. So that's quantum crypto. Okay, so now we'll graduate to a harder problem. This is how to build a teleporter, literally. So there are many processes that do a decay that creates entanglement. So an atom emits two photons, and they end up being entangled. So what I'm showing here is Alice and Bob start together. They have an atom decay. They each get 1/2 of an entangled pair. Then Alice stays on Earth and Bob goes to the moon. What I'm showing is H is what's called a Hadamard transition that makes a superposition, and that circle plus is called a C-knot, a controlled knot gate. So in quantum computing, you can do things like a square root of knot. This is a controlled knot. Quantum systems can't erase, so you have to have reversible logic where you can go backwards as well as forward. So a controlled knot inverts, but you preserve all the information. So Hadamard followed by a controlled knot, we end up with an entangled state of Alice and Bob. Okay, good so far? So then we separate them, and Alice on Earth, then she does, A0 plus B1 is what Alice wants to teleport to the moon. So that's what she's putting into the teleporter. She entangles her new particle she wants to send to the moon with her half of the bell pair. So she does another C-knot and a Hadamard. Then she does a measurement, and she measures what is the state of those particles, which way do they point. And then that dotted line is why I'm going to ruin science fiction for you, because bad science fiction stories, when they need to travel and communicate instantaneously, say, we'll use quantum mechanics. And the problem with that is you can't beat the speed of light. So Alice has to make a classical phone call that takes classical time, and she calls Bob on the moon, and she tells Bob the outcome of her measurement. What Bob then does is prepare an apparatus, and he has 4 choices of which operator to apply. He applies that operator to his half of the bell pair, and what comes out is Alice's particle. Now, a couple notes on that. You can't copy quantum systems. So Alice's measurement, you can't cheat. Alice's measurement destroyed her particle. Meanwhile, on the moon, if Bob was to actually find out what the measurement is, then he would be cheating, and that would be copying, and you can't do that. So Alice destroys her particle. Bob never finds out what the particle is. So this is now okay. But at the end of that procedure, Alice's particle disappeared, and Bob's particle has appeared on the moon. Every way you define it. It came from this measurement, but it is the quantum state, and you can't copy quantum states, so it is Alice's particle now appeared on the moon. That is teleportation. You need a classical phone call, so you don't violate speed of light, but that's teleportation, and this has been done experimentally in labs to demonstrate it. This works. You can't do a whole person, and it's unlikely for another talk's reason, but you can absolutely teleport particles and now molecules this way. Okay, so you graduated from this class. Now let's start using this. So Love Grover back at Bell Labs realized that there was a really interesting group I was part of that would retreat to a Mussolini-era village above Torino, Italy, that worked out the basics of quantum computing. And one of the pioneers was Love. If I gave you a phone book sorted by name, but I gave you a phone number, if there were n entries in the phone book, you would have to look up roughly n entries before you found the name, meaning sorting an unordered list, you basically have to look through the whole list. Love Grover showed quantum mechanically you can do it in the square root of n time. It's not log n, that would actually break a number of things, but it's root n. And what you do is you prepare a superposition of all possible answers, and then you amplify up the right answer, and you can do that in square root of n time. So that's called Grover's algorithm. So in this paper, a colleague and I introduced pulse techniques that have been used across quantum computing. And the basics of it is this, I'll demonstrate. If you have two quantum spins that process at different speeds, you do what's called a tipping pulse, then they start processing. But then if you do a 180 rotation, they do that. And then if you wait the same amount of time, they catch up again and they're back where they started. That mathematically is the same as making time go backwards. So the tipping pulse followed by the rotation formally, mathematically changes the sign of time. And by doing that selectively, you can take a complex quantum system and you can turn off parts of it. So rather than wiring a circuit, you can take physical phenomena and program them. And so we use that to do the world's first faster than classical quantum computation. So here we're implementing Grover's search algorithm, and we're doing it just by programming the dynamics of nuclear spins in spin resonance. And then went on to implement Shor's algorithm. This is one of the most significant quantum things you can do. You can break classical cryptography by finding prime factors efficiently. And so this was a landmark experiment that proved 15 is 3 times 5, but it did it in fewer steps than classical, and it was done by programming molecular spin dynamics. Now, quantum computing gets a lot of attention, but there actually aren't that many important problems. You can do searching, you can do factoring. The really useful thing you can do with a quantum computer is quantum mechanics is exponentially harder to simulate than classical mechanics, because you have to simulate all states of the system. So a quantum computer can emulate another quantum system, was a very important result, and you can do very efficient quantum simulation, and that turns out to be really useful. So, going back to all of this, I won't grade you on the final exam for how well you remember how to make a teleporter, but what does this have to do with your labs? So that was explaining quantum mechanics. Some of the current things in my lab are we're making what are called adiabatic quantum flux parametrons, which are superconducting devices that are a double well potential, And instead of creating and destroying charge in a transistor, you move these quantum states around. And what's interesting is you can do that as zeptojoules. So milli, micro, nano, pico, femto, atto, zepto. Zepto is just above kT, thermodynamic limit, so very low energy. And you're going to hear in a little bit about a quantum Lego AR project. This is a project in my lab where literally the proposal was we wanted to make quantum Lego. So with a colleague, Noray's group at MIT, we're making nanoclusters of tens of atoms, and then we're studying when bricks become bonds, the crossover between mechanical joints and quantum joints to study nanoassembly. So, what does that have to do with you now? When you go in a fab lab, almost every single thing you do is quantum. And one of the goals for today is to appreciate that and start unpacking it. So you just heard from xTool. We love their lasers. Laser is the favorite tool in the lab. Laser light is a fundamentally quantum state. So there's a gain medium. It has discrete quantum states. You pump the ground state to an excited state. It decays to a lasing transition. And then there's what's called stimulated emission, where a photon coming in meets the atom in the excited state, and it stimulates the emission of another photon, and that photon is phase coherent. So it's actually creating a quantum state of light, and that what lets you make this parallel focused beam. And so any time you make a keychain on a laser cutter, you're actually doing a quantum project, a quantum lesson. And I think it'd be great to be able to share what's going on in your laser. When you use a motor, you're using a magnet. Magnets are incredibly subtle quantum phenomena. So magnetism comes from the property of spin I'm talking about. Spin acts like the particle is a spinning magnet, even though nothing is spinning, but mathematically it has the same structure. But magnetism doesn't come from the magnets lining up. It actually comes from what's called an exchange integral, which is an electric property. So there's a wave function for the electrons in the atom, and based on their symmetry, the electric field enforces an ordering of the spin that leads to the magnetism, which is why it's such a robust, strong property. So just using a magnet is a fundamentally quantum phenomenon. We're surrounded by transistors. Transistors are fundamentally quantum. So energy goes as the square of velocity. So as I run faster, energy goes as the square of that. What I'm showing here is that parabola. I'm folding it back on itself. But quantum mechanically, what happens is bands open up of forbidden energies. Then there's a thing called the Fermi energy, which is like the height of a bucket of water if you fill it. In a semiconductor, the Fermi energy is in that gap. Then you can have atoms that either donate electrons or take away electrons, and that's called holes, to dope. And then with that, you make transistors. So if you put a P and an N together, the Fermi energies have to line up, the height of the bucket of water, so the bands bend. And so that's why a diode can conduct in one direction but not the other. If you spread out that interface, electrons and holes combine, and that's how an LED makes light. And then if you have a metal insulator semiconductor, when you put a voltage on the metal, you pull the Fermi energy into the band, and you induce carriers. And so that charge is the variable resistance of a MOSFET. So anytime you're using a transistor, you're using fundamental quantum phenomena. And now we get to a really interesting one, which is you used your phone probably to navigate here, thanks to handy Google Maps. Google Maps was getting GPS data. GPS data is talking to atomic clocks. And what's going on here, Ramsey was a mentor back at Harvard, just a remarkable person. There's a classic atomic clock. There's cesium atoms. I'm showing the energy of the states of the atoms on the left versus the magnetic field. And one state, it goes up, one goes down. So that means if an oven emits cesium atoms and it goes into a non-uniform field, it bends into two streams based on whether they want to go up or down the gradient. Then you go into a microwave cavity, and if you put microwave energy at just the right frequency, you drive the transition between those levels, and you invert which direction they go in the field. So you come back out, you go through another inhomogeneous field, and when you have the frequency right, your detector lights up. And so it lets you find that frequency exquisitely sensitively. And so that's how an atomic clock measures frequency to measure time. Now, when the GPS satellites were launched, they tell you what time it is and where they were. They were called post-Newtonian corrections. And it turns out, we've known from Einstein that when you go faster, time slows down. But even more bizarrely, when gravity changes, time slows down. And your GPS receiver on your phone telling you where you are only works because it's using special and general relativity to correct for time dilation and gravitational redshift on the atomic clocks telling you time. So to use all of this, a few years ago with the US standards body, and shortly you'll hear from the Czech standards body, I ran a meeting on open metrology, on open source scientific instruments. And so one of them is Raman spectroscopy is where you send in a photon and you look at the energy change, and that probes the molecular structure. It's probably the tool of choice to learn about what molecules are around you. And so this is an open Raman spectrometer, similar, not that far off from a laser cutter, but now probing molecular information. The Open Raman project on the right is one in my lab making an open design for a confocal Raman microscope, so you can image as well as measure spectra. This is a really fun one. I love Anton Hughes' group. He's done all these inventive things. This version is making an atomic force microscope, which is like a record player, but it lets you measure individual atoms with the needle of the record player. Here it's showing carbon nanotubes, and it's made just with a few buzzer disks. It's actually a surprisingly easy thing. And so these sort of experiments let you access quantum worlds in your lab. You're using it every day. This lets you explicitly visualize and interact with quantum worlds in your lab with tools that aren't that much different than what you're already using. And finally, just looking ahead to this afternoon, all of this is a mashup of many different disciplines. And so to do this, there's a parallel effort in developing engineering workflows. So there's a lot of rapid prototyping of engineering software, mixing form, function, code, classical quantum to do development for all of this. So let's see, if we go back to here, go back to the first slide. If you're able, let's see, the second slide. Yep. So if we go to the second slide. Okay, so that was a 20-minute version of the class. How'd we do? Okay. And that's the overture. Now, for the rest of today, it'll unpack the last 20 minutes. Thank you.
Thank you, Neil. And up next, we'll have a series of 3 fast talks. The first one brings together quantum mechanics, Lego, and augmented reality. Sounds like fun, right? Our next speaker is the winner of the Good Wall Lego for Quantum competition, and he's here to show us how complex science can be made accessible, visual, and even playful. He's a software developer with a background in physics and complex systems. He's also a fresh FAB Academy graduate, diving into the world of digital fabrication with a growing love for 3D modeling and circuit production. Please welcome a FAB25 stage, Gonzalo Guarner.
Well, okay, do you hear me well? Okay, I hear myself, so I guess it's working. Man, what a venue. This truly feels like a coliseum. So I'm hoping by the end of the talk I don't see many thumbs down. That would be really amazing. So this is Building the Unseen. I will explain quantum mechanics with Lego and AR. And yes, as I was introduced, I'm here because I won the Lego for Quantum competition hosted on the Goodwill platform. So I would like to start my talk thanking all of the organizers, the Goodwill platform where the contest was hosted, also University of Geneva, the CERN Microclub, of course the FAB Foundation too, and finally the amazing organizers of the FAB25, where I personally can say I'm enjoying a lot this time. So just a bit of context of what the contest was about. The idea was to present how we can, with AR and Lego, explain better quantum mechanics, with a goal maybe to make it more accessible for kids, teenagers. But honestly, I believe that it could be useful for anyone. Because really, quantum mechanics starts from the experiments, and not everyone can afford a CERN or a $1,000 setup. So why not use a setup that would maybe cost tens of dollars, yeah, less than $100, let's say. And even if when we're talking about AR, we could just do an app that is practically free. So for the challenge, 166 people participated, 29 were eligible to win. And most of the participants were from the Global South. Yeah. And this is properly the beginning of my submission. So quantum mechanics is infamously difficult to grasp. So that's why I'm so thankful that we already had such an introduction to the topic. Neil, for instance, talked about superposition, where many particles, the particles can be in more than one state at once. There's also the collapse, the particle collapse. When you measure a particle, you see its states changing. And finally, we have also the spooky action at a distance, as Einstein called it, which is the entanglement. I would like to say just one further thing, because we have many examples of how quantum mechanics can be simply unintuitive, because as Neil said, it really does not follow the classical, the macro laws that we are all used to. So this other example is based on the Heisenberg uncertainty principle, and is why this talk is called Building the Unseen. And it's that to measure something with light or an electromagnetic wave, we will use, depending on the size of what we want to measure, we really need this light particle to have the wavelength smaller and smaller, the smaller the particle we want to measure is. So let's say we want to measure an electron. Then we would need a light particle, a photon, that would have a very, very small wavelength. The problem, that the smaller the wavelength, the higher the frequency. And there's the energy of an electromagnetic wave is fully proportional to the frequency of that light particle. So what does end up happening? That the smaller we go, the higher the energy we need in a photon. So in the end, we end up altering the state of what we want to see. Just to see something, we have to move it, which means that at some point, there's a practical limit in the precision that we can have when we're measuring in very, very small ranges. So why Lego and AR can help us get this a better understanding in these quantum mechanics concepts? So first of all, with Lego, we have the physical manipulation that makes everything more playful, more interactive. It has the simplicity and the modularity. So for instance, we could build a QR detection code that could help us as a measurement device, or we could also build just really a mini lab that we could use then with AR to make the experimental setup. So with object recognition, for instance, once we build the thing with Lego, we give them AR properties. And this is where AR comes. And the true magic of it is that we really can visualize digitally what we can't physically. So furthermore, we also have the easy access of it. As I said before, we can have an app that all of us in our smartphones or laptops could very easily download. And some examples that I will show later would include, for instance, a superposition simulation totally impossible to represent physically. Then we could have a particle measurement, so when we collapse the superposition state into just one. Or finally, we could also do, object detection coupled with Lego. So imagine, as I said before, we have the kit, we use AR, and now, just like that, we can simulate an experimental setup. Let's look into that. So first of all, the superposition. We can have a particle that is, at the same time, before we have collapsed it, before we have measured it, in an up and down state. And as you can see, this is the app I built for my submission of the contest. When I play the video, we will see how I can place an object, in this case, an electron that is both in an up and down state. Right. And now, when I get it closer to the QR detector, I will measure the particle, and I will collapse its state. Right now, we went from a superposition state to just an up state. So this electron is an up state. This, by the way, is FAB Barcelona. And yes, just another showcase. This is the photoelectric effect, which is really the studies, the demonstration for which Einstein got his Nobel in 1921. The photoelectric effect consists of a metal sheet onto which we shoot light. What we want from this is that at some point, if the energy in a classical way, so let's say if we threw a very intense torch or a very intense flashlight, we should see electrons popping off the metal. What happens, rather, is that we need a particular frequency. As I said before, if you guys remember, the energy of light really depends on the frequency of the wave. So what happens is that once we pass a threshold of frequency, let's say we go from infrared to, for instance, blue light, which is more energetic, suddenly the electrons pop off. And it doesn't matter how dim, how faint, how small our ray of light it is, we just need that the light surpasses this frequency. So what we see then is that light in this case is working differently. What we see then is that once electrons pop, they have an energy dependent on this frequency. The higher the frequency is, so once we have surpassed the threshold, the higher the frequency is, the faster also electrons will pop, the faster they will get shot out of this metal sheet. So rather than talking about it, why don't we see it in AR? And what we see is me placing the metal sheet. I have a photon, it has low energy, it's just yellow light photon. And as you see, I'm putting it through the electron in the metal sheet, nothing happens. But now I will put another electron that I can modulate. And as you will see, I put it above the threshold, so let's say the threshold is blue, I put it in violet, and yeah, the electrons pop off. And it keeps bugging me a little bit, my OCD, how I didn't fully record the experiment. I need to pop the last electron. But yeah, I couldn't change the slides in time. Let's proceed. So the conclusions. With AR and Lego, we reduce the abstraction. We, again, can see digitally what we cannot see physically. We democratize the access. Again, it's much cheaper, much easier to build an AR setup, also with Lego, than it would require the proper original experimental setup. And finally, of course, playful exploration plus equations will always be better than just equations. So just to finish with the last part of the presentation, I would like to make a little call to action. So what could we do with all of this? What can we really present? How many other things could we do? Because I'm only showing 2 showcases. And then from this, I drew from other great submissions of the FAB, of the Lego for Quantum contest. And we can start with Sarah Khan on the left, where she represented a black hole that is evaporating. She represented the Hawking radiation process, where she placed a Lego board, Lego plate, where then a black hole would have different interactions, especially losing energy through processes that I cannot explain very simply. But essentially, we would have this complicated process visualized through AR. Second, we have Yannick Flieger that did a quantum computing setup, where we can have the different logic gates that, for instance, Neil was showing earlier. And then we can just swap them, change their results, and with AR, we could see what would happen when we would change one thing or the other. And finally, we have the great submission by Saurabh Zamadi, where what he did was the entanglement of 2 qubits on a diamond sheet. And yeah, this was my talk. Thank you very much. Hopefully I'm getting some thumbs up. Okay. No.
Thank you, Gonzalo.
Thank you.
We need to take a photo together because we have matching outfits. I just noticed. Okay, guys. Next up, we shift focus from quantum as technology to quantum as an opportunity. Because as this field grows, the question isn't just about what we are building, but who gets to be part of building it. Our next speaker is working to make sure that quantum development is more inclusive, equitable, and truly representative. She leads equity, diversity, and inclusion at the Dutch Scientific Research Institute, and she's also head of programs for women in quantum development in Netherlands. So please welcome Judith Kreukels. Hi.
Good morning, everyone, and thank you for that nice introduction and for this opportunity to speak here at stage. So I arrived yesterday from Amsterdam, and I was taking a walk here in the park. I don't know if you've been around here, but I noticed there's a roller coaster, actually. And as speakers, we were invited to see the conference hall just the day before. So I was looking for the conference hall, and I entered here, and I saw it, and I thought, oh, nice, there's another roller coaster. It's like turning around. Turns out, it's the stage. So yeah, bear with me while I try to find my balance here. So what does a quantum physicist look like? Most people, they think about this guy. Great hair, right? I think he's not that good at replying to emails, though. But quantum innovation nowadays, it is not something that comes from genius loners in dusty labs. It actually comes from various different teams of people with diverse backgrounds, like these people, with different brains, different talents, maybe even different musical styles. And they just started their internship in quantum at IBM. Quantum technology can solve problems beyond the fastest supercomputers. It's based on the strange but fascinating rules of quantum physics, like particles existing in 2 states at once, as we just learned from Gonzalo, or being connected across distances. At FAB 2025, the organizers know we need collaboration across disciplines to be successful. To turn those quantum lab discoveries into real-world solutions, we also need that collaboration with diverse teams. We need collaboration not only with physicists, but also computer engineers. Research shows over and over again that diverse teams develop better tech. This is proven by research from McKinsey in every report that they show. They are more successful at attracting and retaining talent, making high-quality decisions, and pursuing successful innovations. Yet, diversity is not the only solution. It only succeeds when we work on inclusion and equity at the same time, and when leaders are involved and systems actually change. My name is Judith Kreukels, and I'm head of programs at We in Quantum Development. We are an organization based in Amsterdam that tries to attract and retain talent of underrepresented groups. In short, we are called WICIT. At this moment, we are not yet doing so well if it is about attracting and retaining talent. Especially if we look at the gender balance, it's rather off. To begin with, this happens because not many women enter tech fields. Only 28% of engineering graduates worldwide are women. There's various reasons for that. There's stereotypes, cultural bias, gender bias in education, and what we call the leaky pipeline, where women leave the field along the way. I think it's now 10:05. Some people here are probably in need for their second coffee, and I'm gonna present you some statistics. So bear with me, it's only 15 minutes till the break. As said before, the leaky pipeline means fewer and fewer women stay in the field as they move up the career ladder, as you see in this graph. This graph actually comes from the Dutch network of female professors, and they produce an annual monitor where they monitor all the data from all the universities and universities of applied sciences in the Netherlands. So as you can see, where women account for more than 50% of students, that only moves up to 45% when they become PhD candidates, yet at the full professor level, only 27% is left. You see in the figure as well on the right side that despite tremendous improvements, the percentage of female scientists in STEM is still very low. To put this in perspective for quantum, we see that less than 30% of the world researchers are women. Only 1 in 54 applicants for Quantum World is a woman, and 80% of quantum companies do not even have a senior female role model. This data is only for gender diversity, because we're lacking cultural diversity data, neurodiversity data, and also data on sexual orientation for LGBTIQ individuals. Therefore, there is a high need to attract and retain talent in quantum. Research shows it's actually helpful to have role models. WICIT was founded in 2020 by 2 female researchers in quantum, and they felt a need to support women and non-binary people in the Netherlands who work in industry, academia, and policy. What started as a volunteer initiative has now outgrown to a structured organization, and we have 2,400 members over the last 5 years. What we do? We organize monthly inspirational talks with role models. All our events are, by the way, open for everybody. We have quarterly workshops on equity, diversity, inclusion, and quantum, and we organize an annual symposium. We also offer in-house company trainings and advice on how to hire inclusively. I'm working for WICIT since the 2nd year, 2021, and over the years I had many people coming to me who said, with tears in their eyes even, that they were so happy we existed, because they had never been in a room full of only women in quantum. This year, we rebranded from Women in Quantum Development to We in Quantum Development to reflect our commitment to all underrepresented groups beyond gender. So also sexual orientation, cultural diversity, neurodiversity, and so on. Our aim is to create an inclusive quantum ecosystem where everyone feels that they belong. We want to attract and retain that talent. So, what can you do to attract and retain talent? There's a lot of research done about objective hiring. We know from research at this moment we are not hiring objectively. We are hiring subjectively, because there is bias in hiring systems. What we can do is focusing on behaviors and skills when we write those vacancy texts instead of degrees and formal qualifications. We need to use inclusive language. Research actually shows that if you put up the title of a vacancy text and you include man, female, X in brackets, more candidates are eager to apply. Simple tricks. Also, just using 5 bullet points, it's enough to not scare women off. We need to post job openings where diverse candidates are more likely to see them, and use diverse sourcing channels, so we can post where diversity lives. We need to train our hiring staff on hiring objective and consistent. This means we need to have structured forums where we ask the same questions to all the candidates, instead of going around and asking different questions that cannot be comparable. We also need to diversify interview panels and reduce the bias in them. So there needs to be a diverse composition of people who are recruiting and selecting. Fourth, we need to create a workplace that welcomes everybody, and for that, inclusion training for staff, for all staff members, is needed so that actually when someone enters an organization, they feel welcome and heard. And last but not least, we need to support and grow diverse talent. And what we see is that when we focus on diversity and we get that diverse talent in, people actually don't stay because they feel alone on the work floor, so they tend to leave again. You need to work on inclusion and equity at the same time as that you're working on diversity. So make sure you have role models in place before they actually enter your organization, have mentor programs, but also personal career development plans. Or collaborate with organizations like Wicked. If you'd like to know more, let's connect and collaborate. Scan the QR code or send me an email. And maybe next time we can skip the spinning stage. Thanks.
I'm here with you on that spinning part. The entrance always ends up at the opposite side of where I'm standing. Like really, are you doing it on purpose? I'll be watching you. Okay, to close the quantum section, we'll dive into the world of precision, where even the tiniest detail can make a massive difference. From calipers and multimeters to quantum marvels, our next speaker will take us on a journey to explore where the precision of fabrication tools really comes from. He's a metrologist and deputy director at the Czech Metrology Institute Inspectorate right here in Prague. His work covers almost everything from daily use instruments to national standards of electrical resistance, and even quantum level measurements at deep space temperatures. So please welcome on stage Jan Kučera.
Okay,
welcome.
Thank you. Hi everyone, it's really a pleasure for me to be here surrounded by so many creative people, because that's what we are looking for in the metrology. Have you ever wondered where comes from the precision of your fabrication machines or tools? Probably not, but probably you take a care about the precision, about the accuracy, because when you fabricate something, it should pass into some another object. Or when you are repairing something with some multimeter, for example, you should take care that you replace the old damaged part with the new one with the same value. And that's why I'm here, and I will try to explain where does the accuracy of your measurements come from. This year is not only the year of the quantum technology, but this year we celebrate 150 years of the meter convention that gave the basis to use the same units all around the world. Sorry, in the US, Great Britain, you use sometimes. Yeah, okay. And yeah, measurements for all times, for all people. That's the motto of the metrologists for this year. That's the reason why we go from the kilogram artifact that mentioned Neil at the beginning. Thank you for your amazing, very nice talk. Why we go down to quantum systems? Because the artifact sits at one place and it can be damaged and it's changing the value in the time. But with the quantum systems and with the Kibble balance, we can be precise and we can repeat it anytime. And Brian Kibble, the inventor of the Kibble balance, he learned me something during our cooperation in Quantum Lab. When you are not sure about something, how it works, just try it. That is what I learned from him within just first week of the cooperation. And I'm trying to do it every day in my work. Because what is the goal? We are aiming at some target during our processes. And with low accuracy and low repeatability, we cannot achieve it, of course. So we are trying to have the high repeatability of our processes or measurements. But with low accuracy, you can be out of the target. That was the situation with the kilogram, for example, up to 2019. So we are trying even to perform the higher accuracy to go down to this, what is it, right bottom corner, of course, in the metrology. So we need the metrology, and it's the science of measurement. We define internationally accepted units of measurements, like the SI units. And we realize units of measurements by scientific methods that are reliable. For example, realization of meters through the use of the lasers. And finally, we are establishing traceability for industry, for manufacturers, for scientists, and for you all around. Why? To be accurate and independent in place and time and have the compatibility between every country. That's the goal. Let's give the first example. It's about the dimension measurements in manufacturing. I think everyone, or nearly, most of you are using 3D printers, for example, so what you are taking care about the precision of your printing. So you are using calipers. There you can achieve something like 0.02 millimeters of precision. Or when you are checking diameters, like of filaments, you can use another type of calipers going down to 1 micrometer. So it's something usual that you have on the table in the lab. Or in the case of the fabrication machines, where are some gear systems and threads, we have gear measuring machines, again going down to 1 micrometer precisions. But how to check accuracy of these machines, of these measurement tools? Who is doing that? It's done by laboratories, accreditation metrology laboratories, and they are traced down to national institutes. So what we need for checking? We need the reference measurement systems, of course. For example, here you see the most accurate coordinate measuring machine in the world that is able to measure nearly any shape, dimensions, just by touching the mechanical sensor down to 1 micrometer. Oh, come on, 1 micrometer, it's something that you can achieve with the caliper. But this machine can measure any shape. That's the difference. Yeah, of course, we need to go down. So we use interferometers for length and displacement measurements. Probably few of you here have interferometers in your laboratories too. At room temperatures, at room conditions, you can achieve like 1 micrometer accuracy. But at controlled environment, where you have stable, extremely stable temperature and no air flows, because of course the flow of the air is somehow influencing the laser beam, you can achieve down to 1 nanometer accuracy. Okay, interferometer is using the laser light. So it's a macroscopic quantum system, as you have listened on the morning from Neil. So because it's a stimulated emission with quantum coherence. And here we move down to using of atomic clocks, because the length is derived from the speed of light and time of flight of the laser beam. So speed of light, it's fixed in SI units. It's clear. And time is measurable, so we need a primary standard of time. A few thousand years ago, we have used sundial clocks. Few centuries ago, we have used mechanical clocks. And nowadays, we have atomic clocks. With a femtosecond, frequency comps, traps for atoms, we can go somewhere to 10 to minus something. And for example, in this laboratory, it's a laboratory from Czech Metrology Institute, where our colleagues work on Ytterbium clock. The goal is to achieve accuracy of time measurement down to 10 to minus 16. With Ytterbium clocks, you can be more accurate than with the classical cesium clocks. It's old stylish. Oh, come on. They use it on every GPS and satellite, so we have to be more accurate, of course. And within such system is a vacuum chamber where we trap just one single ytterbium ion down to 0 temperatures to be able to read out from its main resonance frequency the right time. Now let's move to another example, the electrical measurements. Any device plugged to the wall socket contains some resistor, electrical resistor. Even when you put fingers into the plug, you serve as the resistor. Do not try it, of course. So let's talk about the washing machine. It's full of water, full of some clothes, and full of electronics. Of course, there are some printed boards. And when the washing machine is not working well, the repairman has to replace some parts, capacitor, resistor, or inductor there. For example, let's talk about the resistance now, because I'm from resistance lab. You use the multimeter. It has the principle of some measurements, We do not talk about it, but the accuracy of such multimeter, it can be checked only by comparison against some reference, known resistor. So we have some calibrators and resistors going down to 0.01% in accuracy. These calibrators are calibrated against even more accurate devices down to 0.001%. And these calibrators we calibrate at national metrology institutes around the world against the reference resistors down to the level 10 to minus 7. And here, such resistors we can disseminate only from the quantum-based resistor. It's based on the quantum Hall effect with accuracy down to level 10 to minus 9. It's just a very simple, very small device. This one, 20,000 euros if you like one. And unfortunately, this small device you have to place into a little bigger laboratory, in the shielded room. Here we receive the resistor from the customer. We take care about the cleanness and humidity and so on. Then we take this quantum small chip, we place it into the liquid helium or into the cryocooler. We quantize it. It's quantized. It's defined the value only by the fundamental constant, Planck constant and electric charge, nothing else. And together with so-called cryogenic current comparator, we can calibrate the customer's resistors against the quantum one with accuracies down to level 10 to minus 9. Okay, fine, quantum standards and so on. These devices are partially commercial, but most of the work is done by the people, by the scientists in the labs to be more accurate than the commercial devices. So how to realize quantum-based standards? We have to use simple measurement principles, of course, at the beginning, like Ohm's law. But we have to identify influencing parameters. That's the reason why we have so big room around. We have to review the publications, ask GPT or a more experienced community to deal with it. And we involve students, young people, to find new, uncommon and more effective solutions how to overcome these influencing parameters and problems. And then finally, we use fast prototyping in the implementation of new ideas. In the quantum labs, come on, we use some simple stuff, like positioning on the from the 3D printers, isolators, fixing breakout boxes with some plastic parts, or just shielding around multimeters. Finally, we verify the functionality, of course, but we use simple tools to become quantum-based. That's important. I hope I finished my talk precisely on time. When not, I apologize for that.
Thank you, Jan. What a fun talk about metrology. Who would have guessed, right? And that's about it from our quantum section of today's conference. We'll now take a short bio break, so stretch your legs, enjoy your coffee. I see you back here in about 20 minutes. The program will start at 10:40 sharp. See you until then.
Some places claim to be the most advanced, the most connected, the most knowledgeable. But what actually makes a place just perfect? There are always tiny steps behind the big picture. Like when the greatest scientific discoveries start from the smallest things. Yes, it's peas. Our Brno region might not be big, but its ideas are. Bold plans, smart tools, and the drive to break through. There's friendship, if you want to, collegiality when you need it, and closeness with everybody. Long story short, it's like one creative family here. Everyone knows everyone, which is great for sharing knowledge, of course. And the best part is, all these people live in a unique space of 12 universities, top science labs, and modern research centers. The perfect mix for innovative businesses. Because what you do in Brno region stays in, well, the whole world actually. We are the mecca of electron microscopy. A third of the world uses computer antivirus invented here. Many revolutionary innovations from biotechnology and nanomaterials come from Brno. But how did we manage all these big things? It's because of these little things in life, like feeling safe at all times, which is pretty simple when you live in one of the safest places in the world. In fact, our worst natural disaster is this burning stump. Yep, true story. Besides, Brno region has a tradition of being open to everyone. Easygoing, life-embracing, not so touristy, and with perfect prices, they say. Oh, and did we mention everything here is really, really close? 3 capitals are just around the corner. So that's why we don't need to claim we are the biggest and the best. We know that perfect is what feels just right.
xTool, we work to encourage young minds to explore, imagine, and solve real-world problems. Our robots and STEM kits serve as the catalyst to engage students in a hands-on learning journey, to deepen their comprehension and knowledge while having fun. These young innovators can connect with the world and put their skills and characters to the test in our MakeX competitions. The learning experience with xTool doesn't stop there. By offering smart laser cutters and engravers, we simplify fabrication and expand the possibilities for students and problem solvers to unleash their creativity. Active learning is for everyone, so we put our tools in the hands of students of all kinds, from science to art and languages, and from early education to middle school and beyond. With a presence in over 200,000 schools and more than 20 million users in over 210 countries or regions, xTool education makes waves around the world, whether in the classroom or at home. Together, let's bring education to the next level.
Here we go again, guys. Thank you. Thank you. Thank you. Hi. Welcome back after the break. Before we dive into the world of open engineering, this afternoon we will have another round of workshops. And since the pavilions are large open spaces, we'll be using a special sound streaming app to help everyone hear clearly and to keep the noise under control. The app is called Live Voice, and it's super simple to use. All you need is your headphones and the Live Voice app installed in your phone. When you get to the workshop, you will see a QR code on the screen. Just scan it, and that will connect you to the correct audio channel. If you are a lecturer, you'll find a special code on a sticker at the lecturer's table to log in as a speaker and to use your phone as a mic. And don't worry, our FAB25 team will be nearby to help both lecturers and participants if needed. Up next, we have 5 more fast talks from the world of open engineering. And just to give you a heads up, there will be a Q&A session, more like a panel, after all the speeches. So you can send in your questions through the Eventee app. You just have to find the right session for it. In the schedule, it's called Open Engineering Q&A. So find it, tap Ask the Question, and send in whatever you are interested in. And we'll start with a look at one of the most powerful open source tools in the maker world, a parametric 3D design software called FreeCAD. Our next speaker is a real insider, and he's one of its maintainers and a board member of a FreeCAD Association Administrative Board. With the FreeCAD recently reaching version 1.0, he's here to share what's new and what's coming next. So please welcome Hennes. Hi.
Good morning. Thank you very much for having me here. My name is Hennes, and I'm talking about FreeCAD, what's new and what's next. We've been talking all week here at FAB25 about this idea of open engineering, about posting our designs so that other people can share them, can use them, can modify them, can distribute them. And I really want to focus on this idea of modification. Can you modify the design? Because we're not trying to just share these designs so that someone can go out there and make exactly the same thing we've been making the whole time. We're sharing the designs so that these people can go out and can improve them, can maybe make changes that they need for their work, or so that they can make changes, improve your product, and send it back to you and redistribute it and participate in this collaborative open engineering project. And so then the question is, if someone goes and posts a design out on the internet, Can you modify it? Can you make those changes? And there are a couple of different facets to whether or not you can modify this, right? First, was it designed for modification? So a common way of doing that these days is with parametric design. So I've got here a table, here, whatever, somewhere on your screen, there is a table that has a bunch of parameters for maybe a shirt design. And let's say that you don't have little T-Rex arms like I do, and you need to make the sleeve length longer. And so you just modify the parameter, you hit enter, and off to the laser cutter you go. So it was specifically designed with modification in mind. And then the other question is, has it been shared in such a way that, well, you can actually read the file format? So maybe I've given you SVG files. Well, that's all fine and good, except that now you're still stuck only making the shirt that I made, because editing your parameter table isn't doing you any good unless you have the original CAD files. And the original CAD files only do you any good if you have that CAD program. Well, you saw the title of the talk. You know exactly where I'm going with this. I'm a FreeCAD developer, and so this is where FreeCAD enters the picture, because FreeCAD was developed to answer these questions, to provide an open source CAD solution that gives you 3D parametric design. Its development began in 2001, and it's giving you an interface to the Open Cascade CAD geometry kernel. The great thing about FreeCAD, from my perspective, of course, is that not only can you use it to make any kind of design you want without any restrictions about whether you're a hobbyist or a pro user or you're selling your designs or whatever, but FreeCAD itself can be modified, can be distributed. You can use it under the terms of the LGPL. So FreeCAD itself is an open source project, which is great. And I was supposed to click. All right. Well, we've been working on it for about 23 years now, and finally in November 2024, we released version 1.0. So it took us a long time to get there, but we're really proud that we were able to get to version 1.0. But the big question is, what made it 1.0? How did we decide to call it 1.0? So we had talked about it for many years, about this idea that there was one marquee feature that we really needed in order to be able to call FreeCAD 1.0. And here's how you can tell that we don't have a marketing department that's driving our development. And that is because this is the amazingly named and incredibly slide-unfriendly toponaming mitigation. We are mitigating the topological naming problem. Now, the topological naming problem is this idea that if you have parametric CAD and you have a part that depends on another feature, that depends on another feature, that depends on another feature, and you go back and you edit this base feature, and sometimes you're going to break the final feature there. You'll make a change that doesn't work. Well, I say sometimes. Sometimes if you have well-behaved CAD. If you have less well-behaved CAD, it's more like all the time. Right? So this was a problem in FreeCAD. It was a model stability issue. Obviously, we knew about it. We've been working on it for many years. And so kudos to Li Zhang, Real Thunder, who in his Link Stage 3 fork has developed sort of a mitigation strategy, and then to Brad McLean, who took that mitigation strategy, polished it up, added a bunch of unit tests, and brought it into FreeCAD mainline. So now we have a basis for our topological naming problem mitigation. The basis itself provides amazing stability of your models, but it also gives us a framework that we can improve going forward as we add more and more heuristics to our toponaming mitigation. So thank you very much to Brad McLean. I have terrible news, though. Brad actually died about 3 weeks before we released FreeCAD 1.0. So we've dedicated the release of FreeCAD to Brad's memory because of the incredible impact that he made. So thank you very much, Brad, and I'm sorry you couldn't be with us here today. All right. Well, while one team was working on toponaming mitigation, of course, there were lots of other things, lots of other developers working on FreeCAD 1.0, and so there were a few other sort of marquee features that are maybe slightly more slide-friendly. So let me talk about the assembly workbench. We now have an integrated assembly workbench. We've always had assembly workbenches. They've been third-party add-ons you could install via the add-on manager. Now there's a built-in assembly workbench. It is not feature complete by any means. It's still a work in progress, but it has lots of the basic joint types, and it will give you sort of a baseline assembly experience. So you absolutely can use it on your projects, and that's part of mainline FreeCAD. We finally have a unified materials system. And so before, you would set a material in one part of FreeCAD, and it wouldn't be reflected in, say, the finite element analysis or the CAM analysis. So now we have a unified materials system thanks to Dave Carter of Dave's Rocket Shop. So That's a wonderful thing that it may seem obvious. Why didn't we have that the whole time? But we didn't, so now we do. That's very exciting. All right, and of course, we take a lot of flack for FreeCAD's delightful and wonderfully intuitive FreeCAD user interface. We're working on it. We're probably always going to be working on it. My slide here shows you sort of the most user-facing or most obvious feature, and that is an improved theme engine. We're shipping with a light mode and a dark mode, so you no longer have to use the wonderful FreeCAD Classic mode, but you can if you want to. It's beautiful. Oh, chef's kiss. Okay. So what comes after FreeCAD 1.0? Well, of course, developers had no sooner released FreeCAD 1.0 that we began work on 1.1. There are lots of things that are going to be coming in 1.1. Of course, bug fixes and bug fixes and bug fixes and bug fixes, but also things like an improved FEM visualization toolkit where you can do a lot of the visualization where you had to go outside FreeCAD to do it before. Now that's baked right into FreeCAD. We've got tons and tons of improvements being made to the CAM workbench. So if you're a user or wish you were a user of the CAM workbench, you're going to want to check out 1.1. For example, we've integrated the Better Tool library. If there are any developers out there, I think Brad Collette is kind of drowning in pull requests right now. So if you want to review some code, there's a ton happening in the CAM workbench right now, and we'd love to have your input on it. Stealing a page from Blender's handbook, we're adding input hints, so you finally don't have to memorize every single key combination in all of FreeCAD because it's just going to show up on your screen. Yes, it's probably as it always should, but it's open source and somebody had to actually do the work. And we've got an improved hole tool. So again, the sort of thing you're going to see in your commercial CAD packages. We're continuously improving the FreeCAD user experience. At least we think we're improving it. We're working on it anyway. We're making changes. And so we've got an improved hole tool there. So that's your near future in just the next couple of months as we release FreeCAD 1.1. But of course, we also want to take a look at this idea of the infinite future horizon. How can we set FreeCAD up for success for the far future to see what's coming next? And so where do we go from here? Or possibly more important than where do we go from here, how do we go from here? And there's been a lot of focus on that in the FreeCAD community in the last couple of years. First, a group of us have formed what's called the FreeCAD Project Association. And so we're taking in donations, and we're distributing those donations to places where we really felt that money could make a difference in FreeCAD. So, for example, some of those what I call the garbage jobs, right? The stuff that nobody really wants to do for free, like bug triage, or translatable text reviewer, or you're going to hear in just a few minutes from Pieter, our Open Cascade liaison, someone who can figure out whether this bug is a bug in FreeCAD or actually a bug in Open Cascade, which sometimes is easier to fix and sometimes harder, but at least it can go to someone else's bug tracker. So the FreeCAD Project Association sponsors that sort of development. Parallel with the formation of the FreeCAD Project Association, we've also seen some sort of startup of these working groups, a CAD professionals working group, a UX working group, a code quality working group, groups of people who got together and sort of self-formed a group that can then advise maintainers. When someone submits a pull request to FreeCAD, I can ask one of these groups and say, hey, is this code, does this meet our code standards? Is this a good user experience? Is this the way a CAD professional would expect to interact with the code? And so those working groups are spooling up, and we're getting lots of processes in place. We also now have a telemetry add-on, so this is a pure optional, you have to manually download this thing via the add-on manager, telemetry add-on that sends information back to us about how FreeCAD is being used, about what sort of theme you're using, maybe who likes dark mode, who likes light mode, etc. And so if you have a minute and can install it, we'd very much appreciate it. And then last but not least, I'm here. And part of the point for me being here at FAB25 is to improve our relationship with open hardware teams, because it seems pretty clear that it would be wonderful if open hardware could be using open software. But we understand that that's not always possible. There are some roadblocks, some stumbling points, some things where, wow, FreeCAD's just not there yet. And so I'd really, really like to hear from the open hardware teams here. I mean, I'd like to talk to everyone, but I'd really love to hear from you about what sorts of things are stopping you from adopting FreeCAD, and how can we, especially we, the FPA, start to get us past those things. So please reach out to me. I'm going to put on my flame-proof suit in the back here and come back out for a Q&A. So please hit me up with your questions or your comments. Otherwise, thank you very much and enjoy the rest of the talks.
Thank you, Chris. And as Chris mentioned, he'll be joining us later today for a Q&A panel. So if you want to ask him anything, just send it to our Eventee app. There is a special session called Open Engineering Q&A. So just ask the question there and send in whatever you're interested in. And we are staying with FreeCAD for one more talk, but this time we are diving deeper into how it can support open source hardware at scale. Our next speaker is a self-employed open source software developer and researcher with a background in high-performance computing. His work explores how to make open source hardware easier to document, share, and build, and how can FreeCAD play a central role in that mission. To tell us about designing true variant parts for open hardware comes Pieter Hijma.
Thank you. Thank you for the introduction. And yes, I would like to take you along on my journey to trying to improve open engineering. And it has 4 ingredients. First, inspiration. I'm a Fab Academy graduate at Waag Future Lab. That's the first ingredient. The second ingredient is some funding. I was funded by the startup Onsel that tried to create a cloud platform with FreeCAD, actually. Unfortunately, they had to shut down, but there is also, Chris talked about this, the FreeCAD Project Association that has also funded my attempts. Then the third ingredient is support and help from the community, and the fourth ingredient is trial and error. So, but I'm going to talk about variant parts. What are variant parts? So suppose you have this model and you want to, you need a profile, an aluminum profile. So you create a sketch, and then you want to extrude it, you have a certain length, but then you realize, I need a second one as well, so with a different length. So you create a copy of it, and yeah, you change the length, and now you have those 2 profiles with different lengths. Well, great. But then later on in the modeling process, you realize, I need a little bit more detail. Suppose you need to have holes in the corners as well. So you change the sketch, and yes, we now have these holes. Oh, but wait a second. Unfortunately, it's only in one of those copies. So do I now have to go and change the sketches of all those other copies? Well, without variant parts, you indeed have to do this. But with variant parts, the idea is that you can define what you want to vary, for example, the length of it, and nothing else. And if you have true variant parts, these changes will automatically propagate to all the other instances. So why are those variant parts useful? So I'm a big proponent of open source hardware, and the fact that FreeCAD does not have true variants is a big limitation in reuse and modularity of components that you design. So, and I have actually an example for that inspired by my Fab Academy project, my course there. So, and I had this problem in many of my projects, but I created a life-size slide for my kid with the CNC, and it has this wedge and a crossbar, and if you look carefully, then you realize that the holes for the wedge and the crossbar depend on the thickness of the stock material. So this thickness, so here you can see the crossbar going through, and it's also in the steps. You need to know the thickness of the stock material. Okay, no problem. So each of those parts have a parameters, thickness of the stock material. So, but suppose you're designing without having the stock material available yet. Then you get the stock material, you measure it, oh, it's 50 millimeters, and now you have to go into all those parts and change the stock material to 50 millimeters. That's a bit annoying, of course. You would like to have a global parameter that governs all these parts. So, and this is perfectly possible in FreeCAD. You create, what I did, I created a separate file with a global spreadsheet, and all those parts were referring to that spreadsheet, and when I had this stock material, I would change at one spot, and all the parts would change. But this is a big limitation in the modularity and the reuse. So, for example, if I load this panel into FreeCAD, it automatically opens this, you see the red circle, a different file that has these global parameters. And that is annoying, because if I want to share this panel, for example, on a cloud platform, and people want to download it, and they don't have this second file, then it won't work, it will break. So this is a big limitation, and if FreeCAD has these true variant parts, then this would be no problem anymore. So, inspired by this, I tried to solve this, and this is where the trial and error part comes. So I was talking to Ansel, and sharing on a cloud platform is very important, and my ideas drove them to hire me for this, and I created a first addition to FreeCAD. It's called FAR-sets, and it was a success, because this was merged in, and now FreeCAD has these FAR-sets that were going to be the basis of these variant parts. So then I created a second pull request. I wanted to have my code accepted by the FreeCAD community, but unfortunately, this one was not accepted by the community. You can see that it was a large change, 1,500 lines of code, and based on the funding that I got from Ansel, I could do basically a very limited implementation, and I agree that the implementation that this pull request had really limitations. And the FreeCAD community also realized maybe this is not really an Ansel thing, but maybe this is a FreeCAD-wide thing. So maybe it's better to request a grant from the FreeCAD Project Association. So I did so. So I created a grant proposal, but unfortunately, after long discussion, so the point is that you can't read it because the discussion on the page is so incredibly long. And by the way, my screenshot software gave up on me and said, you have to tell the audience that there's 1/3 more of this discussion. So there you go. But yeah, so this was gracefully declined. Actually, Chris Hennes, the previous speaker, was the one giving me the news. So that was a bit disappointing. Well, this grant was not accepted. But I had a long video meeting afterwards with one of the founders of FreeCAD, Jorik van Havre, and another community member, and they gave me feedback, and they said, well, maybe you can chop it up in smaller pieces and maybe make it more like a research project. So based on that feedback, I submitted a second grant called Research Variant Parts, and this was funded, and I've already completed this project, and it resulted in a prototype that provides these true variant parts to FreeCAD. So I want to give you a demo of this. So I have here a bar, and you see this purple property that is a bit special, but yeah, you can use it to change the length, nothing special here. But then there is this special V button, the purple button, and you can click this and create those variants, and you can change the length independent of the other ones. Okay, great. But now I realize that I want this bar to be wider. So I go into the sketch. This is a top view, and I want to make it wider. So I change the sketch, make it wider, for example, 140 millimeters. Now I want to press the OK button, and yes, all 3 instances make this change. So that is good. It's exactly what I want. So, but this is only a prototype. I would really like to get this into the main line of FreeCAD. So how am I going to do this? And this is where the FreeCAD community came in and was very supportive. We have an amazing group of developers right now, and they realized that, you know, if we want to make some progress, we need to get these larger code changes in. So, well, yeah, so it's 140 millimeters now. So the community, specifically Casper Donat, came up with something called the FreeCAD enhancement proposals, inspired by the Python enhancement proposals, which gives kind of a more formalized process to make these bigger core changes into FreeCAD. And this slide is already out of date. It's not proposed, but it's now active. And to give you an idea, here we have the workflow. So you can come up with a draft. There is a discussion going on among the developers. It goes from proposed, and it can then be withdrawn or rejected or accepted. So we have now this process in place, and this is the way to go, I think, for these variant parts as well. So this was a little insight into how I try to improve open engineering, in this case in FreeCAD, and it had these 4 ingredients. Some inspiration, I got inspiration, perhaps frustration at my Fab Academy course that I did at Waag Future Lab, thanks to the whole Fab Academy community for being very supportive, thanks to Waag and especially Henk, Bas, Erwin and Sako, who had to put up with me. Thanks for Ansel providing the faith to hire me to try to implement this, and the FreeCAD Project Association as well. Thanks to the FreeCAD community to come up with this nice process. And yeah, it was lots and trial and error, but I guess this whole community knows that this is probably the only way to do such a kind of thing. So thank you for attention, and yeah, please come talk to me if you want. Thank you.
Thank you, Pieter. Okay, our next speaker unfortunately couldn't be here in person today, but he still wanted to share his talk with all of you, with FAB25 community. So we will now play a pre-recorded video where he tells you what happened, and then he explores a fascinating topic at the intersection of sustainability and technology, bio-based electronics. To give him a proper introduction, he is a researcher, educator, and a co-founder of Arduino, with a PhD in interaction design and a background in telecommunication engineering. He's also helped build several labs in Malmö University, where he teaches subjects ranging from creative coding to embedded systems. So please enjoy the special contribution from David Cuartielles.
Cuartielles, and I'm here today to talk about bio-based electronics. I will briefly introduce myself, but first I will tell you why I'm not there today. I had planned to come to FAB25 by bike, and this was my agenda. I was going to be riding through Europe, passing Berlin, Prague, Berlin, then going to Brno, then back to Prague with the Maker train, and then all the way back to Sweden, where I live. Unfortunately, a small bike accident left me like this, so I got 11 stitches, and I couldn't ride just to.
Sorry about that. We tried to fix the sound. And then we'll try to play it again. But now let's go to our next speaker. And it's someone who builds tools, not just for making things, but for learning, exploring, and reimagining how we design. He's an independent researcher and open source tool builder with dozens of projects under his belt in digital fabrication and creative coding. Right now, he's focused on building fundamental CAD infrastructure for the next generation of design tools, tools that are open, transparent, and built for makers. So now, let's find out who owns your CAD tools and why does it matter. Please welcome Leo McElroy. Hi.
Oh. Is it possible to see it on this screen as well? Okay, great. So it's really a pleasure for me to be here today because the Fab community and Fab Labs are very dear to my heart. When I graduated college, the first thing I did was start traveling around the world, visiting Fab Labs and doing projects with people. And I went all over the place. Some of you may recognize yourselves in these pictures. And I slept in a lot of Fab Labs. I do want to take the opportunity to suggest that we add a bed and a spare room to the Fab Lab inventory. And I would encourage all of you to make use of those around the world. And I ended that year at the FAB conference in Egypt, looking at this stage, well, not this stage, but the equivalent stage there, and watching these talks. So now I'm here to tell you what I've been up to the last 6 years. I have been building tools. Many of these tools I built at an edtech nonprofit called Hack Club, where I came up with this scheme to give teenagers around the world access to creative technology in exchange for them building projects and sharing them with the world publicly. So this was the first project that launched this program. We called it You Ship, We Ship, and this project was Sprague. And to illustrate how it worked, we built this creative coding environment online, also with teenagers, and then kids would build projects in it and submit it to a gallery as a PR. And when those were accepted by the community, we would then send them a kit of parts that they could use to build this game console, and then they could play their games and everyone else's games. So it's like a game console you can't buy. You can only get it by actually contributing to the ecosystem. And we've had around 1,000 contributors to that project over the last few years. But more importantly, the whole program has grown into dozens of projects that tens of thousands of teens interact with every year now. And of course, I didn't forget about digital fabrication. So we had to do one to introduce people to CNC machines. In this project Blot, you would create a generative art piece and then submit it to an art gallery, and we'd send you a machine that could draw it. And in fact, I really didn't forget about digital fabrication, because all while I was doing this, I was also making open source design tools. For some reason, I have a strange compulsion to do this. So I build lots of tools. You can see some of my tools here. In the top left, there's a tool for embroidery design. Below that's a programming language for parametric line drawings, really designed for laser cutting. There's some super specific tools, like this lithophane maker, where you can turn images into stacks of paper that project the shadow of the image. There's a whole series of computational pottery tools, which I built with Lingdong Huang. And the most developed of those is this block-based programming language that you see in the bottom right. And today I want to tell you about two specific lines of inquiry that I've been following building tools. One of them is a series of electronics design tools. This tool may be familiar to some of you because I've shared it with the FAB community before. It's called SVG PCB. I started it with Quentin Bolse, who's up there, and now Chris, who's sitting right next to him, has also become a contributor, and Rico has contributed as well, who's here as also. And what makes this interesting is it's a circuit board design tool where the whole circuit is described in code. But coding can be kind of hard, so you can also draw the circuit in this special bidirectional editor, and it will write the code for you. And now you have a parametric circuit represented in code, and if you edit the code, or if you edit the drawing, the two will stay synced with each other. And you can see, actually, the project in the top right, made by a How to Make student at Harvard a few years ago, was actually featured in one of the research papers the other day. It's a flexible circuit that would be quite hard to make through other means. It was designed in SVG PCB. But many people find coding hard, so of course I also had to make a GUI-forward PCB editor. I think the name SVG, designing circuits by trying to figure out what pins do what and connecting them to each other. It abstracts the schematic into this high-level block diagram that has interfaces like I2C, SPI, just a general-purpose GPIO, and you connect those things together, and it will automatically do design rule checks and electrical checks. Here you can see an example of it running. So this is all in a browser. Almost all the tools that I show you are. There's no logins. They're open source, of course. So here I'm generating a board. It creates the file, and then of course you can open an SVG PCB if you don't want to use your browser, if you don't want to leave your browser, or I know that it's a little bit of obscure of a tool, so if you prefer to use KeyCAD, you can download it and use Richard's submodule layout plugin and have this reasonably complicated circuit generated in about the time that you saw there, that was only sped up by 2 or 3. And of course, you also need to make those circuits, so I had to write a milling tool. Or if you don't like to make circuits at all, you can use this other tool that Jake and Quentin, once again, and I worked on, where you can assemble these circuits that are already made in software and build integrated systems out of that. So I had all these circuit design tools, but if you think about Fab Academy, maybe half of it is making electronics, maybe a little bit less than half, and the rest of it is building physical things. So I started thinking, well, how could I make these physical modeling tools, solid modeling tools, like Fusion and SolidWorks? And when I started looking into that, I found something really interesting, that there's this core technology inside of these tools that was actually developed by a very, very, very small group of people back in the 70s and 80s. And these people started a couple companies, like the same people started multiple companies that have now been sold to the big companies that make the tools that you recognize. And the consequence of this is that not many people actually really understand how this technology works. So a geometry kernel is, like Open Cascade is another example of this. That one's a little bit different. But that's basically how 3D shapes are represented. I'm specifically referring to BREP kernels. So these are for solid modeling, which is what you would need for doing mechanical design. And another one of the ingredients is constraint solving. So you could think about this as the thing that powers the sketching systems in your CAD tools. And in that case, the story is even simpler. So when I ask who owns your CAD tools, I'm not actually wondering who owns the IP for them. The answer is, a good guess is normally Siemens. What I'm wondering is who really understands how these tools work. And I'm interested in expanding that understanding for more people. So last year I quit my job and decided to focus full-time on constraint solvers because it seemed the easier of the two, to be honest. So I read through all the literature on constraint solvers and figured out what separates the few open source ones, which do work, like the one in FreeCAD, but they're distinctly different from the commercial ones. And I started implementing all of these. I went through all of them, and what is the point of this? Well, now you can start to build tools that work a bit differently, that use constraint solvers differently than the way that they're typically used. So here you see an origami design tool. I'm drawing a base pattern as a stick figure, and it's in real time generating a creasing pattern, which you can see simulated here. I know that's quite quick, so I'm also using the constraint solver in the traditional way, where I am constraining the sketch itself, but it's also being used for the creasing engine, and it's using these inequality constraints that you may not have access to if you're just trying to use an off-the-shelf solver. And just to give, interestingly, actually, that origami simulator is also written by a CBA alumni. Just to give an example of that to show, I have this creasing pattern. I can print it out, fold it, and then shape it into something. And if you want to use that, I'll post a link for that as well. And of course, I also had to make a 3D modeling tool. So I was inspired by when you make CAD models, oftentimes the real product of doing that is sketches, like they're orthographic views of the thing that you're making, and that's kind of the ground truth that goes to the manufacturer or the machinist. And I thought that's really interesting, so I wonder if we could make a tool where we just draw these views, and once again use this constraint solver that I can now use a bit differently because I've made it myself to link these sketches together in different dimensions and model the whole object just by just with constraints. So there's no like feature tree in the traditional sense. It's all just parametric constraints. And this is also using a different type of representation for the geometry called FREPs, which I won't get into now. So what's the takeaway here? Well, I think that tools shouldn't just be open source, but they should actually be understood. And making things open source is a great way to do that, but also a great way to understand tools is to try building them yourself. And when you understand tools, you can not just recreate existing tools, but you can make new tools with new capabilities. Also, I obviously find it super fun, and I would encourage you all to try it. People occasionally ask me if I have social media to follow the work. I do not, unless you count GitHub. But because I thought that question might come up, I will start an email list. So if you want to join that, you can scan this, and I'll try to let you know when I have experimental tools that you can test. I'd also love to hear what sort of tools you would like to build. Thank you so much.
Thank you, Leo. Just a reminder, we'll bring Leo back on stage for a shared Q&A. Eventee is still open if you'd like to ask him any question. But now, we turn our attention to one of the most powerful open source tools in a world of digital creation. a tool used in everything from films and video games to 3D modeling and animation. We are talking about Blender, of course, a platform that shows what's possible when open source meets world-class creativity. Our next speaker has been part of the journey for over a decade. Today, he is the COO of Blender and General Manager of Blender Studio, helping lead the platform's growth while keeping it open, community-driven, and cutting-edge. So please give it up for Francesco Sidi. Here you are. Hi, Francesco.
Hello, everybody, and thank you for having me here. And I really like usually to start by showing rather than saying what Blender does, because I think it's much better to let the community and the people who use the tool to actually speak for what it's capable of. And it's one of the little things that I do as part of the Blender project that I feel like it's my contribution to go online and find some of these videos and look for ways to showcase. So I reach out to artists that I see and I'm like, oh, your work is so cool, I want to put it in a Blender reel, can I use it? And usually people are very friendly and they lend their work so that then this brings more awareness of what Blender can do. So we have a few minutes to talk about the project, and I want to share a few stories. And before we start, just like a very quick question, especially because I love this venue, this all around. I want to know who knows Blender. Maybe this is a bit discounted, so people know. Curious about people using Blender. That's like a data point that I'm trying to collect over time as Blender grows in popularity. Who's been using Blender for the past year? And for the past 5 years. Who uses Blender for more than 10 years? Okay, there are a few people that have been there from the beginning. So I think that bringing some history and some more awareness of what Blender does is going to be interesting for you. This is, Blender, as you know, is this 3D content creation tool. And it is free and open source software. It's pretty popular nowadays. What you see here on the screen is the director of the film Flow. Recently, earlier this year, won an Academy Award for Best Animated Film. It's a good demo, in my opinion, of what Blender is capable of. This is how a modern 3D workflow looks like. When using Blender, you have like a high-quality viewport, and you can just operate on something that basically looks like your final work. Of course, not all creative workflows are like this, but this is something that has gotten Blender to be incredibly popular in the past few years because it really enables artists to see what they're working on and what they are going to deliver as efficiently as possible. a few use cases for Blender. So as I mentioned, and as you've seen, Blender is used for films, feature films, like a bunch of them. Some are still coming. Is used for making TV series. In Blender, we keep track of user stories. So like, what else do people do with Blender that is not just film and animation, which is kind of the primary initial idea for what Blender was meant for. It's used for product design, to create high-fidelity digital mockups. It can be used for asset creation, for forensics, so like forensic reconstruction, or for journalism purposes, for machine learning and synthetic data generation, for AI training. So this is an example of using CG to create dangerous scenarios. So for example, a train track where you want to drop obstacles on, that's not what you want to train your computer vision's algorithms on real life data. You want to simulate a tree falling on the train track and not do it for real. It's used for research. So this is a paper from Disney about neural motion rigging, so basically AI interpolation for animation. And even in these very powerful and very well-funded companies, Blender is used as a sandbox for playing around and showcasing the technology because of its accessibility, its availability, its powerful Python API. It's very easy to hack. This is like a final set of images that I just love. This is a historical reconstruction of Tenochtitlan, which is the ancestor of Mexico City. This is another beautiful thing that you can do with the software, like create images of the world that is not there around us anymore and give us a glimpse of what was possible, what was happening back then, and have really large-scale, high-quality visualizations that serve very educational purposes. Automotive industry uses Blender for all sorts of things, especially in the design process. And I want to highlight a quote from a Blender conference session from a couple of years ago, that car design will benefit from individuals and companies coming up with their own tools. The point of being able to customize and tailor the tools to your own use, that's really the future. And this is kind of a result of also Blender being adopted by all these different kind of communities. So I'm gonna skip this and get to some introspection part, because as you have seen, like Blender is doing well, is used for many things. It actually recently celebrated 30 years of being around as a project. A few years ago, we did a birthday campaign to collect gifts, so people could just give a little present. We got like 10,000 presents for Blender to kind of help the funding. And we have a development fund platform where generates almost 200K a month. So it's like a respectable amount. This allows for a large team to work. The Blender HQ in Amsterdam and online, so 50 full-time people, hundreds of volunteers, thousands of occasional contributors, over 12 million downloads a year. So basically, it's success, you could call it, right? And there are all these applications, everybody uses it, like very good impact. Basically, we are the heroes. And so you can either die a hero or you live long enough to see yourself become the villain. So how do you become the villain? And so you can do some things like pursue quick popularity, make compromises, use the community, just be evil. But we actually want to be good. So, and this is a little bit more the focus. So what do? You want to focus on your product and your mission, have sustainable funding, and set up a good governance. So a couple of, getting a little bit more into these points. So for the principles, let's really make sure that we have a good mission, that it is clear. So what is Blender about? And the mission of Blender is to get the world's best 3D technology in the hands of artists as free and open source software. Because we envision a world where everybody is free to create 3D content with free technical and creative means and free access to the market. When it comes to the vision, here are just a couple of quick examples. I want to talk about one that is, I think, also relevant for this audience, the parametric design versus the use of AI. So you guys have seen probably these MCP demos where people type a prompt somewhere and that drives Blender to do stuff. This is one of the modern ways of using AI to control digital tools. It's a little bit scary. It's, at the same time, it's like basically you are telling someone to use Blender to do something. And if you have ever tried to do that, you can find that there are some inherent limits that are very difficult to overcome, because no matter how skilled the person that you're giving instruction to is, they are not able to read your mind. So there is always this element of latency and understanding and context that makes these kind of things difficult. On the other end of the spectrum, I don't know if I'm trying to go to the next slide, but that doesn't advance, so the clicker doesn't click anymore. Maybe someone can advance the slide for me? Actually, the whole screen has has paused, so we are in a frozen moment in time. So I have 1 minute and 21 seconds to finish. And actually, I can take all the time that I want. I can go on also without, if you want. I can just speak. 30 seconds to fix the program. It just froze. Yeah, that's no problem. So what we are going to see once we resume is kind of the opposite thing. What do you do? Like, how can you use parametric tools and procedural tools to achieve creative output? And basically the idea, like you're going to see in a video, it's essentially an artist came up with a system that combines grease pencil. Grease pencil is a tool for drawing 2D strokes into in Blender. A lot of 2D animation is done this way, a lot of design and sketches are done this way, and you can combine that with geometry nodes, which is a procedural geometry engine, which basically allows to essentially generate geometry, and you drive this with these geometry nodes, with these grease pencil strokes to do crazy stuff. So basically, really like free-form design. It looks much better than the way I'm describing it. Okay, there you go. So let's go here. I'm trying to, there, okay, there we go. Here, all right. So this looks like, you know, nothing like a 3D model that you can actually pose, rig, and deform. It's actually, as I was saying, I will just go through the video very quickly. But you can see it's like all these 2D strokes that then are controlled by this procedural geometry generation system. And that's kind of like the contrast that you have between this. Instead of saying, okay, prompt and generate, you actually generate, but in a parametric way and have control. So you can do really, really creative and fun stuff this way. And speaking of proceduralism, another classic example is, of course, this kind of stuff, parametric system that allows you to simulate any kind of construction and destruction and so on. Another vision for the product vision and focus, I want to highlight the extension platform. Blender recently built a platform where developers can share extensions. So Blender does a lot of things, but there are very often thousands of specific use cases that is not so practical to include into the software design itself. So you want to make sure that Blender can be extended to fulfill those needs. And we built a platform that is fully dedicated to hosting free and open source software. And this is like an example of a tool that, you know, it's downloaded 100,000 times since the time it was posted there, and it helps people to do 3D printing. Briefly touching on the topic of funding, because that's like one of the other important things. How do you keep yourself sustainable? So, and people always ask us, how do you guys make money? And we do it in 3 main ways. One is individual funding, so like through the development fund platform, which I mentioned, we get like a lot of donations. And I want to tell a very quick story about this because it's kind of funny. Like last year, we did a campaign called Join the 2%. So basically, we say if only, you know, we have 1% of the users that are donating to Blender. If only 2% of them would donate, how beautiful the world would be. And so we did this campaign, Join the 2%. And this is like our funding graph. So you see we introduced this one-time donation. People can do a little gift, and you see a little peak. And we were all happy and went home for the holidays. During the holidays, something happened. There was this giant spike of donations. Like, what happened? The campaign was done. We thought we did good. Something actually now is exploding. And that's because somebody on the internet decided to make a clickbait video called, Why is Blender in Financial Trouble? With a giant Blender logo and say, our fault. And I was like, you feel sometimes a little bit bad because we are not able maybe to generate that much response. At the same time, these kind of more controversial statements are possible to do by the community. So guilt-tripping the community into supporting Blender is something that the community can do. We don't do it. But it's just kind of to highlight the point that empowering the community to do this kind of stuff then can lead to interesting results. On the flip side, there is, of course, like more work that we do with corporate funding, so build relationships with different kind of organizations. You may know some of these logos, and it's essentially making sure that the industry comes on board and supports Blender. And a quick note on that is that I very often emphasize putting content before technology. Very often companies still put the technical advantage as their competitive advantage. And what we always try to advertise and explain is that like Blender, open source software, that is like the foundation that enables everyone to work, and then it's up to your team, to how creative your team is and how they use the tool to do their work that actually makes the difference. And finally, I also try to do more institutional fundraising, going to EU meetings and trying to lobby for getting open source to be better recognized and more supported. Blender does annual reporting where you can find out more about all this stuff. And finally, a quick word on governance, which is just making sure that you have sustainable and well-organized leadership of the project to make sure that things kind of can keep going and you don't have like one point of failure in the management of the project, and make sure that your community is empowered. This is a graph to me that speaks a lot about the power of the community. It's like the time that it takes to solve an issue when you report it to Blender in the bug tracker. It's a stat that I love to show. So you can see that the majority, like half of the issues get usually resolved within a week or so. And even more impressive is the time to get a response, which is like in a day. So this really shows the scalability and the power of the community working together to help each other and make sure that when you're using the tool, you actually are connected with people. And in fact, this is all about people. It's just like, you know, there's also the reason why I'm here, why I attend this kind of, why I attend this meeting, and I'm very excited to meet and get to know everybody. This is a picture from GDC San Francisco earlier this year. We went into a field with a big Blender flag, started waving it around and see if people would come, and that's then what happens. So that's the magic of the community, and that's the magic of Blender. Thank you so much for listening.
Thank you, Francesco. I thought I hacked it. I didn't. Francesco will be joining us for a Q&A session. But before that, what we often hear or even say inside of the Fab Labs, tech is fun, right? Mistakes are part of the process. Well, we apologize for the technical difficulties, but we really would love to try one more time to show you the clip from David Cuartielles. So fingers crossed, we get to learn more about bio-based electronics. Let's roll the video.
Hello friends, this is David Cuartielles, and I'm here today to talk about bio-based electronics. I will briefly introduce myself, but first I will tell you why I'm not there today. I had planned to come to FAB25 by bike, and this was my agenda. I was going to be riding through Europe, passing Berlin, Prague, Berlin, then going to Brno, then back to Prague with the Make It train, and then through the other all the way back to Sweden, where I live. Unfortunately, a small bike accident left me like this, so I got 11 stitches, and I couldn't ride just one day before departure. Luckily enough, no bike got really hurt during this process. It was only me. I absorbed all the hurt. So with this, I want to say hello to everybody, to Neil and the Fab Foundation, to my friends who I would love to be hanging out with. And I will just talk about why I'm here. Well, I'm here because I'm a teacher at Malmö University and I'm one of the founders of Arduino. In particular, I'm responsible for the shape of the boards and the first bootloader, among other things. As you know, Arduino is this open source development platform that includes Creative Commons documentation and a very interesting and widely used IDE, which is also GPL. And people use it to make a lot of stuff, from game consoles to stitching machines to fuel controllers for rockets. So Arduino is being used everywhere, but I came to talk about our concerns with the future and sustainability. So as part of Arduino, I'm also working as head of research with the Desire for EU project, which is a very interesting project that is looking at designing and recycling sustainable electronic boards for European circular economy. This is a very big name, but in essence, we're looking at is analyzing how the life cycle for components and boards themselves is, and what could be done to make more sustainable electronics, to improve the electronics market and make it more long-lasting. So we look at the research that exists. This is, for example, a view on research made up to halfway of 2024. Papers published, and you see there is an increasing amount of science being produced. And our concern, of course, is how to make the SDGs reconcile the electronics industry. And the SDGs, as you know, they aim at making the world a better place by making it more equal and better for everybody, so that we can evolve as a society as a whole. So if we look at how different people are looking how to make this better in the electronics industry, we see, for example, what ST Microelectronics is doing, and they propose a 5-steps process to improve the electronics market. We from Arduino think we can contribute by looking at the product development and the manufacturing. We can make better designs, and they can be manufactured in ways that will produce less carbon emissions. So there is 2 existing processes that I think we can improve. One is the repurpose of electronic components, and this is something that is already being done by different people in different ways. On the other hand, we can look at how to dispose biodegradable parts. And currently in electronics, there is no biodegradable parts. So what we are suggesting is the use of bioreactors to dispose the PCB, but having the PCB being made instead of with epoxy and glass fiber to be made with PLA flax. PLA flax is a combination of a fabric and PLA as a glue that will make a new type of substrate that could be decomposed using these bioreactors, as I mentioned earlier. But this will require revisiting the different processes that are needed to manufacture the printed circuit boards. So there's hundreds of processes in making boards. We're talking that just in a factory where we manufacture our boards in Venice, there is 70 processes that the board has to go through before it comes out the door. I'm just going to highlight 2 of them. One of them is the CNC machine, where you have to you make the different holes, biases, and also mechanical holding holes for boards. And this requires drilling, and drilling heats up, and drilling different materials requires also being attentive to how drill bits might break and might degrade. On the other hand, there is the process of etching, and I will remove myself from the picture here so you can see this is the etching line of where most of the Arduino boards are made. Those 2 yellow cranes, they are taking PCBs up and down and dipping them in acid so that the copper that's not going to be used will be disposed away. And then the thing you see in the front that says shadow line is actually a washing line where thousands of liters of water are used to clean up the boards. So these are 2 of the processes, and there is one more which I wanted to show you because it's very interesting and unknown by people. This yellow cupboard you see there is actually an oven that is used to cook the boards at 100 degrees for an hour after applying the paint. The paint is actually cooked on the boards, and that's why it's so durable. It's not just painted and then let dry. Okay, it dries at certain temperatures. And as you see, all of these things I mentioned, they require heating, either through the drill bits or through the oven, or they require interaction with acid. Okay, this keeps this in mind because PLA is not going to work really well with those. And then, of course, there is other processes that are harmless, such as, for example, testing. Is done with robots like this one that is testing with 8 tiny arms all of the electric connections on boards to make sure they work properly. On the other hand, there is the assembly line where you get the PCBs and then you put the components on them. And the assembly line works through a pick and place machines that put the components in the right positions, and then they go through an oven where the soldering paste is heated up and gets to make sure the components end up soldered at the right locations. And that soldering typically happens at 300 degrees, which is again far over the melting temperature of PLA that you know is 220 degrees. So as you said, there is many of these processes in factories that are not really welcoming PLA as substrate material. So what our project is looking at is changing all of that. Finally, just to brag a bit about Arduino's processes, I would like to show you this. These are actually testing machines that are used at all of the Arduino factories, or the factories where Arduino works with, because Arduino doesn't really own any factories. So we put these machines to test every single board that comes out from production and make sure that they work as they should. So what I'm saying here is that new materials, such as PLA, requires new processes, but it doesn't necessarily require getting rid of the machines. The machines are going to be the same, but what we will do is to use less aggressive acid. We will use lower temperatures for soldering. We will use a different chemistry for soldering. And in this way, we will be able to produce boards that will be based on this PLA that could then be decomposed easier. Because FR4, the current material for electronic boards, is basically indestructible. So it will last hundreds and hundreds of years. Some aspects of these boards. First of all, the granularity of the material. Here you see a microscope view of a cut of a board. These boards made with PLA flux, they are a lot more granular than FR4, which means that when you drill, for example, there's a lot more material coming out, so drilling has to be done differently. The drill bits have to be clean after each drill, which is different from the current FR4. Also, the plating of the holes is different because the material is more porous, so it's harder to get things to stick to it in the same way. On the other hand, soldering cannot happen at 400 degrees or 300 degrees. It has to happen at something around 160 degrees. But the chemistry for this already exists, so it's not like it's anything new. It just has not really been applied in a production line systematically as we want to do. So it's the science is there. So with all of this is where we are today. So Arduino, thanks to the collaboration with BME, one of the partners of the Desire for You project, have already produced this board, which is the Arduino Nano and the Arduino Nano Uno, Arduino Uno. And you will see that there are some differences in the design, and those are key to be able to succeeding at making biocompatible boards. You have to change the design guidelines when you design. For example, just to give you a tiny detail, if you look at this particular picture here, you will see that there is 2 biases for every bias. So there's two holes for each single bias. So that's a way to ensure that the biases are properly connected. So it's kind of important to follow these guidelines. And here, if you want to take a picture of this, these are the guidelines that we suggest for biocompatible boards as of today. This is evolving, it's in constant flux, sorry. We expect this to be different by the end of the project, which is 2028. So there's still research to be done. For example, when it comes to composting, as I said, these boards are biocompatible, which is not the same as biodegradable, but we're aiming at proposing tests and systems for future biodegradable boards. And currently we're testing the boards to be composted in external compost bins, but also in a laboratory compost setting with in a temperature and humidity chamber. What you see in the bottom left is a worm eating a board. This was very happy to get this message from Attila, the coordinator for the project for the Budapest University that's collaborating in the project, when he said, oh, here's the first worm documented eating an Arduino board. So hopefully in the future this will be the norm. So our goal for 2027 is to have 4-layer boards that will be able of doing HAI, which means smart processors on board, and do wireless communication. And we're obviously already working on the design for this. And yeah, here you can see some pictures of the draft. This picture is only lacking the antenna that is being developed by Grenoble University and will be placed there. It will be the first Arduino board with onboard antenna and LoRa communication. So we're formulating 2 new principles based on our research. These are more the theoretical aspects that I think would be great to discuss in this panel. One of them is the idea of cold manufacturing, referring to the idea of lowering the temperature in the machines that are currently used to manufacture in normal factories. We want to use the same factory, changing the chemistry, lowering the temperature, which in the long run will have a lower CO2 emission. And there is experts in life cycle analysis looking at this to make sure that the new chemistry is actually not worse than the current chemistry, so that we're sure that what we're suggesting is solid. On the other hand, we like to talk about just enough technology. We think that we need to design things that are enough for the task and not oversized for the task. It's very common to do things that are oversized for the task, which means using more resources and more consumption of energy, more CO2 emissions. By changing our mindset towards designing just enough for the task, we will very likely end up with more sustainable designs and products. So with this, I just like to tell you guys to stay tuned for our participatory user studies. During 2026, we will produce over 1,000 boards that we will ship out for people who would like to test them. We'll announce everything on the Arduino website, so stay tuned, and I hope we will have a great debate. And again, I'm really sorry I couldn't join you for this. Hopefully, I will be with you in FAB 26 and FAB 27 and whatever other FABs come in the future. See you soon. Thank you so much. Take care and bye.
Great talk, great video from David Cuartielles on bio-based electronics. We hope you enjoyed the video, and hopefully he will be soon okay and back on his bike. But now the stage is ready for our Q&A panel. So please welcome back on stage Hennes, technology educator and FreeCAD developer, Pieter Hijma, open source software developer, Leo McElroy, independent researcher and tool builder, and Francesco Sidi, COO of Blender and general manager of Blender Studio. Welcome back, gentlemen.
Thank you.
A lot of questions from the community, so let's start with the first one. What are the future plans for Blender, and what is the next point of focus?
Who do you want us to answer?
Well, Leo, you can, if you want to.
I think it makes it more interesting. Like, I would love to hear what the guys here think it should be, because it's always very fun to hear what people say. I think you should do this. I love to hear that. So I can say it later, but I think from your perspective, you guys know Blender, we talked about it. So like, you know, to keep it also relevant to this conversation, I think from your perspective, what should be the next thing for Blender?
But the next thing is hard. I love Blender. I use Blender all the time. It's one of my favorite tools. FreeCAD steals user interface ideas from you all the time. I love to see that the Blender user interface continues to evolve towards a sort of ever easier to get into standpoint, right? It is a tremendously powerful tool with 11 trillion buttons, which is great, but the discoverability of those buttons, you've been doing such a good job of getting them better. I would love to see that work continue.
Yeah, that's it's actually a very common, in a way, feedback to improve accessibility of the tool. And for the project, I think there is always this striving, this balance between having new features, pursuing new ambitious goals. I kind of briefly touched upon some of in my presentation, talking about these procedural parametric tools, which under the hood they have extreme complexity. How do you make them more accessible? How do you make them more usable? But then also, how do you make sure that you don't alienate power users? Because you want to keep that balance. So I think that that is like one of the big goals for the project. And then another one that I want to briefly touch upon is new platforms, in the sense of like bringing Blender to new places. Right now, Blender works on the PC, and today there are different computing platforms, for example, tablets or VR headsets, where content creation is possible, and it gets more and more powerful and more exciting to use those tools. How do you bring a tool that was a software that was designed in the 90s with mouse and keyboard in mind to a place where you don't have those things? And so, like, these are the kind of things that we try to think about for the future. And of course, keeping this big machine that is 30 years old still running and not collapse into itself, which is a big part of open source development and software development.
Okay. What is the future for FreeCAD 2.0? Chris, Pieter.
That question sounds so familiar. Francesco, would you like to answer for me?
I have something to say, because like I've been, of course, you know, at Blender there are people that love fabrication and design and parametric design. So I have seen the tool, and I think that the path where the project is on to really build a bit more kind of brand awareness and like presenting, like outward facing, like getting out of this loop of, okay, we are doing this thing for ourselves. It's great, because that's the scratching the itch, right, of the open source. But like try to be a bit more outwards. I think that brings a lot of benefit. That's what builds powerful community and involvement and helps you to grow more. And I think that in the broadest sense, I think that that's what I hope happens. maybe a bit high level. Like, because feature-wise, I think you always have, right, benchmarks, and you always want to do, there are other softwares out there that do stuff, so that's not so interesting for me. It's more on the community side.
Yeah, and obviously the FreeCAD Project Association is very interested in community and building community. For FreeCAD, what we're really focused on, or what we're really interested in, is building this community, not just of users, but of course the hope in open source is you're a user and you decide to become a developer. That's how many of us joined. Many of us joined because FreeCAD made us very angry. Right? That's open source. That's certainly how I got involved, is FreeCAD did something that screwed up my model, and I said, I'm going to fix it. And I don't even remember what it was, but maybe I fixed it. I hope I fixed it. That would be great. As for FreeCAD 2.0, it's hard to say. Actually, one of the things we're talking about in the community is not having a FreeCAD 2.0. One of the challenges we ran into in 1.0 was this idea that we pushed and we pushed and we pushed, and we had a deadline and we wanted to hit that. And we ended up then merging some code that maybe could have used a little more polish. Yeah. So we would maybe like to have less pressure on developers to try to get the next huge feature in, and let's take our time and let's do things right and sort of release maybe quarterly or something like that. So Pieter talked about FreeCAD enhancement proposals. There's one out there right now that is live that we are discussing that very thing. So I have no idea what the next big feature is, because it kind of depends on what the developers decide to develop. We'll see.
Pieter, what is your take on the future of FreeCAD?
Well, I would like to have the variant parts, of course, yes. So that is one step, but also, yeah, I talked about Ansel, and Ansel was a venture capital-backed startup, but it had to shut down, unfortunately. But the cloud software is now open sourced, and I just received, I submitted a grant to NLNet to continue working on the Lens platform, and it was granted. So I hope maybe in a year or so we have a nice platform to show also content, FreeCAD content, and be able to exchange that, and maybe we go a little bit into the direction of Blender then, and can show what FreeCAD can do. So I hope that will be a good point for the future.
Leo, there is a great question for you. How do you ensure open tools stay user-friendly for beginners while meeting advanced needs?
Yeah, well, I think all of us could speak to that.
You can, yeah, all of you can participate in answering that.
I do have some thoughts. I think making a tool for a specific purpose. So for me, I mean, maybe Blender in particular has done a lot of great work in the last few years, improving the UI, UX, but I think developing tools in conjunction with projects is one of the best ways to assure that they're designed well. And so as a technologist and maybe as a programmer, it's very common to have the inclination to generalize things, to make it the tool you can use for anything. But when you build a tool and you use the tool at the same time, then you can really hone what it's for. And I think that makes a better tool for users ultimately.
Okay, would you like to add something?
I want to mention that indeed the model of content-driven development, that's something that Blender has been doing for many years. The idea of bringing artists and developers together to work on creating something, and then that's when, things actually happen, because you have the real world, the real life use by people that are definitely not developers. They don't care about your developer problems. They want their creative problems to be solved. And that's the best reality check that you can get as a tool designer and as a tool developer. So definitely.
What
I was just going to say, one of the things that inspired me, I've been to Blender headquarters, and you guys have the studio right there with developers and people making projects all the time.
Yeah.
It's really clear just from how it's set up that you guys believe what you're saying.
It's challenging, though, often to communicate this well with the community, because very often this model has been challenged. Like saying, but why? I don't care about the movie. I care about my one feature that I know how it should be, and only me, and I don't care about anyone else. Make my feature now for free. I don't donate, but give me the feature. And there is a lot of that. Of course, that's not the majority, but like making sure that that narrative is well understood, that's like actually a challenge, especially now with the Blender Development Fund, which is more generically aimed at developers, and say support like core development, make sure the maintenance can happen. All those things are also important, so then you also have the tension between, okay, keeping things stable, making releases, supporting platforms, and doing new things. So it's something that I really strongly believe in. It's been embedded in Blender's nature for the past 20 plus years, and I definitely want to keep doing it because I think there is a lot of value to it. Yeah.
Francesco, how can we use VR and AR in Blender now and in future?
So there is a technology called OpenXR, which is an open spec to basically integrate and support VR headsets. And there is initial support for a few years for this kind of technology. So tethered to a computer, you can simply wear a headset and get into this scene inspection mode where you can basically work together with someone else that is operating the computer. So you have very limited capabilities of interacting with the software and the virtual environment. And that's a start, and we definitely want to focus on some key things. One of them is, you call it location scouting, VR location scouting. It's kind of a part of digital production. So as a film director or a director of photography, you want to be dropped into this digital world, a digital set, and then you have a camera inside of the digital world, like a little screen inside of the big virtual screen where you are. And you can look around, and you can take snapshots and pictures of locations. And that is then very helpful for someone that is maybe not so technical or technically inclined to navigate in 3D and manipulate the scene with a computer, but just actually to be in it and simply click a button. This is the kind of stuff that the direction where we're going to with VR, because that's the kind of first steps, right? Moving around. So we take it one step at a time.
Mm-hmm. Francesco, what do you think about technical and mechanical designs in Blender?
It's something that is asked a lot, and sometimes to the fault of saying, guys, there are like so many other tools that are designed for that. How about, people want Blender to do everything. It's very powerful, so to an extent you can. I think that very important is to have good interoperability between software, so that then you can make the best out of the open source tools that are out there. For having, for example, more interactive things, you can use Godot. But if you want to do more like high precision CAD style modeling, print out blueprints, fabricate, like you may want to have FreeCAD or some other software. And so I think that obviously there are some uses, and I think that interoperability is very important as a topic to answer that.
Guys.
I have one thought on that. Is that, like, one of the fundamental problems is there aren't really data formats for watertight geometry that you need for modeling mechanical stuff. So it's hard to add it to tools because it's not even really entirely clear what you would be adding support for.
Yeah, like connecting these two worlds, is a challenge. But I think it also is because as open source independent projects, you're usually so focused on getting the core of your stuff right that outreaching and connecting and figuring out solutions is overhead. Yeah. And so, again, that's for me so important to be here and to meet with people and connect, because that's like definitely, this is not game making, this is not filmmaking, this is something much closer to what you're talking about. And these things never happen unless you actually sit down and talk about this. Yeah. So, yeah.
Peter?
Yeah, cool thing is, I guess that Blender and FreeCAD, the two projects inspire each other as well. So, for example, in the world of architecture, there is a standard. It's called IFC, and Blender had an architecture module as well that supported this data file format, and that inspired Jorik van Havre to try to implement that into FreeCAD as well. So. I believe it's even the case, I'm not completely up to date on this, that IFC files can be opened both in Blender and in FreeCAD. So yeah, so there is, there is inspiration from both projects. Also in indeed user interface, yes.
And of course, you can load FreeCAD files in Blender right now using Sverchok nodes. So I mean, you can load up Blender and open a FreeCAD file if what you want is to render something.
Chris, interesting anonymous question. Will FreeCAD be free forever?
Oh, that's a great question. And the answer is yes, absolutely. And the reason that I can say that is because the FreeCAD project was set up from the very beginning by Jürgen Riegel and Werner Meyer and Jorik van Havre to make sure it could never be unfree. It is licensed under the LGPL, but there is no single copyright holder. Every individual contributor to FreeCAD holds the copyright to their changes to FreeCAD. There are hundreds, if not thousands, of copyright holders in FreeCAD. There is no practical way that anyone can actually get all of those people to agree to relicense FreeCAD. Certainly, you could not possibly get them to agree to make it non-free. So yes, conclusively, FreeCAD will be licensed under the LGPL forever.
Thank you for the answer. No one, yeah. One last question for you, Leo. We know you've been on a year-long tour of global maker communities. So what's one lesson or moment that really stuck with you?
Oh, wow. That's a hard question. There are so many moments. I mean, just the generosity of people. Like, I'll tell a story about Jens, who's here, actually. Coincidentally, so Jens was also a Fab nomad. Where is he? Over there? Over there. Jens was also a Fab nomad who I had no idea that he existed. And when I was going to a Fab lab, one of the first labs in Lyngseidet, way up north, above the Arctic in Norway. And I flew to Oslo to get there. And I was so excited to get started, I just looked up the closest makerspace, and I walked in, and there was Jens. And first I told the people there, yeah, I'm doing this world tour. They said, where have you been? I said, well, I haven't really been anywhere. I've only been doing it for 2 hours. And they said, oh, well, we got a Fab nomad too. And they introduced me to Jens, and we became friends. And we decided to do a project together. So I went up north, and then I came back to Oslo. And Jens, he actually had to go away for a little while. And he just gave his life to me. He gave me his apartment. He gave me his bike, and he even gave me the project he was working on, building this machine for Oslo Innovation Week, which was how I started learning how to build machines. And it was just such amazing generosity from somebody who I barely knew, and I'm really glad that we're still friends today. He's visited me in the States. It's such a delight to see him here, and I had that sort of experience all over the world. Yeah.
This is what the community is all about, so thank you for sharing. Thank you guys for giving us such a great insight.
Thank you.
Chris Hennes, Pieter Hijma, Leo McElroy, and Francesco Cidi. Thank you guys. What a great Q&A panel. Wow. Okay, and now we dive into a conversation that zooms out. From Fab Labs to cities, from makers to systems. This panel is called From Fab Lab to Fab City to Full Stack. And it brings together innovators and change makers from across the Fab community who are applying the full stack methodology to drive real transformation in their cities and regions. The Fab City Foundation is at the heart of this global movement, helping connect cities that are using digital fabrication for local production, circularity, and sustainable development. The vision: cities that can produce everything they consume, powered by makers, data, and collaboration. Today's panel features voices from across the Fab City network, all working at the intersection of technology, education, local ecosystem, and policy. So let's give them a warm round of applause. Kate Armstrong, CEO of Fab City Foundation, will be hosting this session. Please welcome her on stage. Hi. Hi. And we would like to also invite to the stage Josefina Nano, Daniel Ingracia, and Stefan Papst. Hello, guys. The stage is yours. Hi.
Thank you for the warm welcome.
Mike is all yours.
Thank you. It's our pleasure to shift the focus, as was introduced, to deployment. And we've heard some incredible speeches this morning about the technologies that are behind the stories that we're about to tell about how we at Fab City are looking at changing the fabric of our neighborhoods, our cities, and, as you'll hear, our bioregions. So this panel, as was introduced, will go through stories from our network that talk to the ways in which we can be makers within our cities, but also be change makers within our cities using the technologies that we know and love and explore at events like this Fab Festival. We're going to be using the Fab City Full Stack, which is the Fab City Foundation's theory of change. So many of you will be familiar with the computational idea of the full stack, which talks about development on multiple scales. So we've taken this idea, and this has been published, including in the winning paper, I will say, from the FAB event this year by Thomas Vevanko. This has been published as a way for us to conceptualize what is needed to turn the power of an individual Fab Lab or makerspace into change-making at a global scale. So that's what we're going to be looking at. As you can see by the schema, which is shown on the screens right now, it moves through different scales. So we move all the way from the tooling at the bottom, your Fab Lab, your makerspace, all the way up to the sharing knowledge at networks. So this is particularly interesting for us at Fab City. Many of you may know that we have a network of cities. At the moment, we're 54 cities. Some are represented on the stage here. By the end of the day, we'll be 56 cities. So please come to our pledge, which is happening after this panel. That cities network allows us the opportunity to, much like you share information between Fab Labs, share information between cities, city leaders, and champions who are really pushing forward these ideas in their cities. So we're going to hear from some of those champions today. We have 3 incredible speakers that are going to talk through each stage of this full stack. So we'll talk about the tools, the methods, and the spaces. And I hope what this will do is pique your interest, give you some idea about what we're doing at Fab City, and we will be around for the next 2 days. Please come, or 3 days, please come and speak to us, grab a beer, grab a coffee, and see in which way you can bring this kind of thinking and systemic implementation to your city, region, and beyond. So, let's start with tools. Daniele, the floor is yours.
All right. So, hello everyone. My name is Daniel Garcia, and I basically was a graduate in Fab Academy in 2015, which changed completely my career from, a computer scientist sitting in a desk to build such large machines like this laser cutter that you see on screen. I mean, as Kate has been introducing, you need the tools in the cities, and the tools allows the city to produce what the city needs. And I think spun off from this philosophy a long time ago, I decided to build my own laser cutter. So the choice was, okay, shall I buy a laser cutter or shall I build a laser cutter on my own? And basically, the first motivation was I hadn't had enough money, to buy the laser cutter, but also I wanted to learn everything about how the laser cutter works and how I could transmit this knowledge to others. So basically, when I moved from Italy to Germany, I went to a small university, the Rheinwald University of Applied Sciences in Rhine-Westphalia, and they left me the key of the lab, and they say, okay, the lab is yours, you can come here anytime off work, and you can do whatever you like. And that's the story in about 10 years, started 10 years ago about LaserDuo. So LaserDuo represents our first open source machinery, is a large format laser cutter, where I did a lot of naive mistakes, like putting screws like 10 centimeters to each other, and there are like 2,000 screws in the machine. But what happened was that basically somebody from the Helmut Schmidt University in Hamburg came to visit us, saw this machine and said, oh, we have to replicate this machine in Hamburg together with students, and we have to demonstrate how this open source hardware process makes it possible inside the Fab cities for others to replicate this machine. So the story of this machine turned out quite differently. I mean, it was not working in the beginning. It came to Fab 14 in Toulouse, and it broke down, and somebody here, like Cesar, I don't know if he's here, helped me building it, helped me fixing it. And so what happened is that I used this machine as a production tool in my company, machines, for about 5 years. And now this picture that you see here, it's something that gives me goosebumps every time I see it, because this is the German National Museum of Technology, which is now hosting this machine as a permanent exhibition of what can be done in Fab Labs. And I hope that these kids that you see in the picture and everyone that passes there can be inspired on what can be done in Fab Labs. So, so I also, it's very important for me to mention that I love to be here, and I am nothing with you guys, and many of you inspired me, like for example, Jens was one of the first one, was mentioned before, I think, that inspired me, Jens Divik from Norway, to build machines, Nadia Peak, Neil, of course, the Fab Academy, and so on. So after producing parts for our city or my company for 5 years, this machine still works, and if you go to the National Museum of Technology in Berlin, you can use it yourself under the supervision of the museum. So in the previous slide, instead, you see our outcome for our cooperation with Fab City, for the Fab City Hamburg project. So these that you see on stage are 3 years of sleepless nights of about 10 people. Maybe some of them are still around here. And the Open Lab Starter Kit is basically a full inventory of open source machines for Fab Lab. So this that you see on the screen, it's something that was never done before, meaning like you could have your own Fab Lab with fully open hardware tools that you fully know how to build it, how to modify, how to repair them, how to work with them, how to build them with other people, and so on. So in these 3 years, we basically took the Fab Lab inventory and we made it completely, fully open hardware and open source. So what you see on screen are basically 8 different types of machines which cover the whole range of things that you can do in Fab Labs. For example, we have small and large format CNC milling machines, small and large format 3D printers, vinyl cutter, which is the only open source vinyl cutter out there, by the way, 3D scanner, and so on. So, and these machines that you see here are already getting used in many parts of the world. For example, in Ukraine, we have 2 small laser cutters. So you imagine, like in a war scenario, how open hardware can win. Yes, because, for example, the laser source comes off Amazon and costs $100, or they can find in a local shop. So the machines, of course, broke down many times because they're installed inside the mobile Fab Lab. They were taken off and showcased. And then what happened is that they were able to fix it, and still they are running after 3 years of work. So that's the power of open source. But, I mean, we have great representative of open source software around us, and they made great features in their software. In these machines, there are as well very advanced features. So there is one of the first open source tool changer for the CNC milling machine, if you're willing to have a milling machine with tool changer. We have a multi-laser laser cutter. We are so open source that we'll have developed our own Linux distribution dedicated to machine control, which is called Open Lab operating system, which you can use on your machines. And as well, we have a nice GUI that you can operate in touchscreen. The machines have monitoring camera, Wi-Fi. We have multiple lasers in the laser cutter. And we even have made G-code generation for the laser cutter for you to directly generate the job inside the laser cutter. So as we are talking, this machine are already on GitHub, released as with the Open Hardware CERN license. So every one of you is free to go there, build them, replicate them, or if you have questions about how to build this machine, please reach me out. So the project is actually finished, and now our goal is to penetrate even more the city with open source hardware, for example, by making more industrial-oriented machines. So currently, so this year, next year, we're working to make a low-cost, open-source metal 3D printer. So to convince more industry partners that open source is actually just not, for small machines and desktop or hobbies, but also for more serious tools. So if you're interested about machines, we also have a book, which we are going to give out, I think, on the end of the panel, where you can learn a lot about how to build machines written together with Jean-Michel.
Awesome.
Thank you.
Yeah, thank you, Daniele. So in this very, very quick snippet of the incredible work that you do and the collaboration you have with Fab City Hamburg, we see 2 levels of the stack. So we kind of see that tooling, and then the next, which is how that tooling integrates with the city fabric. Josefina, would you like to take us through how these tools become part of methods for how we implement change in cities?
Yes, of course. Thank you, Kate. So my name is Josefina. I'm a programs lead at Fab City Foundation. I come from a background of architecture, urbanism, and I got connected to this amazing movement through IAC and Fab Lab Barcelona. So jumping in directly to the methods that say dimension, I think we can go back to the full stack. Okay, so basically the method dimension includes 3 layers, right? So we have layer 2, which is enabling new forms of learning. We have layer 3, which is incubating value-generating projects. And we have layer 4, which is orchestrating efforts between local communities and different initiatives, right? So going over to methods. Okay, so I'm going to jump over to 3 case studies, which actually represent many of the things we do in Fab City, which is amazing, and we do it with Kate and an amazing team. And the first case study, hopefully we have the representative here. I don't know if Sad is here, but basically this project is an MDDI alumni, Sad Chinoy. And basically, he got graduated last year from MDDI, which MDDI stands for the Master in Design for Distributed Innovation, which is a hands-on learning program that we implemented and developed in Fab City, IAC, and Fab Lab Barcelona. And basically, this program is focused in the intersection of design, technology, communities, and ecosystems for interspecies well-being. So basically, SAD's project, which I think if you haven't met SAD, reach out to him because he's an amazing human being. Fantastic, there he is, spotted. Okay, so, SAD's project, I'm gonna read it so I do not forget anything, but basically his project, labeled Eat My Microplastics, aims to challenge the perceived inaccessibility of making meaningful things using digital fabrication. I think this is a great question, right? So, through the strategic use of active community participation and hands-on learning by doing, he developed a series of engagements proposing around the growing issue of microplastics. So basically, he was working closely with a community and creating this awareness and developing, of course, many things in between. But I think this is a great example of the interconnection and the interdependency of the 3 layers. So then, jumping over to the second case study, this is one of the winning projects from the Fab City Challenge in FAB24 in Mexico. I don't know if you know about this project, which is amazing, basically. And just a quick summary, the Fab City Challenge, it's a global collaborative program we implement and develop in Fab City that basically brings together different global and local agents, people, to propose meaningful responses to urgent, let's say, cases in different areas of interventions. So this winning project called Biodiverse Cities, Reinventing Boundaries in Coexistence by Leila Yunis. I think I saw Leila as well here. There she is, amazing. Andre Kijanek, Sad Chinoy as well, Selene Perez, and Eliton Mereyes de Mora. Apologies if I have not pronounced correct your names, but this was an amazing initiative developed in Monterrey. Basically, Monterrey is a city in Mexico which is quite industrial, and it's connected, it's surrounded by mountains and this huge biodiverse environment. And basically, the citizens have been disconnected from what's happening in that biodiversity. So this team basically developed different tools to monitor what's happening in that ecosystem and bring this knowledge back to the people, back to the community. So amazing initiative. If you do not know about it, you can reach out to Leila and also Sad about it, which they can debrief you a bit more on this. And then jumping into the last case study. So this is more recent. Basically, I think we have Robert as well. So this is one of the winning projects from the Fab City Awards of this year. Every year we have a different edition of the Fab City Awards, which is an award in which we as Fab City, we support projects that are building the conditions for regenerative, locally productive, and resilient futures in cities and regions. And basically, this winning project was granted for the category of Best Community-Led Climate Action. We have Robert Garita here. I think he's going to represent this as well. And this is CIFI's Fab Lab in Costa Rica, basically. And this initiative is a digital fabrication lab in La Carpio in Costa Rica. And basically what it does, it empowers youth and residents through skills training, entrepreneurship, and inclusive production. I'm going to go over some numbers. So we're talking a Fab Lab of 900 meters square for community space, so this is huge. We have 350,000 volunteer hours, 2 active social enterprises, and basically in here makers are generating income locally. So this is another amazing initiative that we aim to give them a voice in this ecosystem. So yeah, this is it from the methods, and I think they're all interconnected with other layers as well.
Thanks, Jose. That's awesome. This gives us an incredible example. Oh, thank you. This gives us an incredible example and snapshot of the 3 layers in which the Fab Labs and these makerspaces start to integrate with initiatives and prototypes within the city. So this is an incredible way in which we can see these makers become change makers within their communities. So thank you for these examples. And a quick shout out that the awards will be presented in a panel also coming up during the program. So finally, we're going to go to the top levels, and this is a very exciting moment because today we actually have the pledge from our new region, our newest region, joining the Fab City network, and Stefan is representing our new region. So we're very happy to have you here to present this, and welcome. Thank you very much for sharing your experience.
Yes, thank you very much to be able to be here. So I will also just quickly introduce you to our project. Going back to the layers, so we are Fab region, and we are in the higher layers. We are kind of in between the sheets. We are from the the German region of the Berger City Triangle, which consists of the cities of Wuppertal, Remscheid, and Solingen. And we are trying to be basically bring together the bottom-up approach and the top-down approach, which is very challenging. But as you can probably see, we have, our region is a bioregion formed from the geography. It's a very mountainous region, let's say, for Germany at least, with very many valleys where the cities are located. So we are actually having, just from the regional development, having the challenges that there's not much space to grow actually. And in these regions we are trying to develop the basis for a circular economy for these 3 cities, And we are not, as I said, not a bottom-up approach, so we are trying to analyze the networks and institutions that are already in place and try to bring them together and work together so that the 3 cities together can become a Fab region still in the making until this afternoon. So I didn't bring really case studies, actually, more like examples of what we're doing, because we are really having this challenge that we are facing or that we are having to work with very different levels of the Fab region at the moment. And we're always saying, or I'm always saying that there are actually 3 kinds of actors in the region. There are the ones that are really hyped and that were already hyped when we started the project. Then there are the ones that don't really care, that we would like to work with, but they don't really care. They don't see a value in working with us. And a large number of actors that are in between. They don't really know, they like us, but they don't really know what they can gain from us. And it's very important to really analyze where these actors are standing, focus on the ones that are hyped, and really show the value to the ones that are undecided if they want to work with us. Because in the end, you need to show value. You need to show, we need to show that we don't create more work to them because they are all very busy. And this brings us to the issue that all our projects also are based on very different levels and for different stakeholders. We analyzed three, let's say, focal areas of work. First one is textiles, the next one is food and agriculture, and the third one is actually construction, where we want to work and analyze the systems, and in the end be like a leverage factor to help these areas of the economy and society to become more circular and less linear. So the first just example I want to show you is our work with the GESA, which is a social institution that is taking care of our textile waste. They're collecting waste and would like to see what's still reusable, repairable, and recycle these textiles to bring them back to society. And as you can see, we just have big piles of trash basically there. And we still don't know how to handle this because there's just so much trash, textile trash that is being collected. We are now sitting on around 300 tons of textile trash at the moment. For example, I had just one day of working with them together, like we really went there, saw what's going on, and we just opened up trash bags with them together. Basically put our nose into them, see how the smell was, if it still was good to be recycled or not, and then just really open up the packages and just collected them really manually, which is much more work. We knew there was a lot of work, but how much trash we actually have, like textile waste, it's just really hard to imagine if you have never seen this. And working one day with around, I think we were like a group of 10 people working with them together, we basically were able to open up one day of collection. It's this huge waste, but also potential. We are still trying to find ways to process. And here comes also back to the work, what we're actually looking for, what we're actually trying to achieve. We're looking to build networks, find people that actually have answers, working also together with the University of Wuppertal, for example, make hackathons to really find machine solutions to the actual problems that we are having. And I think this is where also the makers movement is actually one of part of the solution. We need to find the actors in society that want to work on solutions, not just like for theoretical or hard or like problems from the heart, but really build solutions, cheap solutions, locally manufactured, that can help also solve the problems that we are having in society and also the economy of the FAB region. One other project we are having is our sense boxes, also inspired by FAB Barcelona. We wanted to get also into education and education systems to sensibilize students and teachers alike, not just for our work, but also what they can actually do, like citizen science. These sense boxes are boxes with different tools that they can measure environmental impacts of our society, of our region, basically, in our regions. So they can actually, see that they can do science. It has a lot to do also with just, giving competences and showing people that they can become competent in natural science and technologies in the makers movement, gather lots of data also here to eventually help them find solutions for our region. And this was also just like with talking with people. We need to, as our project, as FAB region, it is very important, or has been very important, to first also get to be known in the Bergisch Triangle. Because, with makerspaces, you're normally seen because you have a physical space. Our FAB region, as we're not even located in one city, we really get also in the heads of the society around us. And one of the ways was to go into schools, to go into learning facilities, and also use the students there, the teachers there, as vehicles. And then also make them become trainers, workshop leaders, and therefore get some leverage because we are also a relatively small team, actually. And it's very important to facilitate more makers, more facilitators, and more change agents in the region. So that's what we are, where we are at the moment. And so thank you for this.
Wonderful, thank you, Stefan. So we have an extremely comprehensive, I think, example and case studies that take us through the different levels of the full stack. And I think it shows the way in which each layer is indeed its own, but is connected to others. So in particular, I think it's quite interesting in your case, Stefan, with the bioregional approach, because your organization has brought together 3 different cities that sit inside a very specific bioregion. And that specificity of natural resource, natural environment impacts directly the way in which these 3 cities are able to function, and of course the resource capacity of those cities. That's where the bioregional approach means that as a city-based organization, we can expand to the natural world and the systems that are, of course, sustaining for us as humans, but also many of the aspects of our cities that are non-human. So I think this is wonderful, and you're also joining, of course, the Fab City network today, so that's why really exciting, which is this top level, which is this sharing information. And I actually would like to start there with some questions. We have some minutes to go through some questions which have arisen during the talk, and I hope that maybe if you had similar questions, we are going to answer those now, but we might do a little bit of a rogue Q&A at the end, but let's see how we go. So I think one thing that came up in all of your talks is this idea of engagement, stakeholder engagement, and the interconnection between different organizations globally. So I'd like to ask you, Daniele, to start off with, how does that work on a functional basis? How do you actually engage with other people in other cities or locations? You talked about Ukraine, you talked about Hamburg. How does that work for you?
Yeah, so, well, first of all, we are nerds inside the lab building the machine. But we learned to be a bit more communicative. And I mean, for sure, the Fab City infrastructure in Hamburg has helped me disseminating these open hardware machines. So what we do is basically we found contexts and scenarios where open hardware can be of key value. So for example, we tried to deploy these machines in places where replicability or spare part findings or, for example, knowledge transfer to the other cities is very important. Therefore, for example, again, this scenario in Ukraine, but we also have several machines in Tunisia, in North Africa. Now we are trying to set up a lab in Nigeria, or we deployed some of this machine in another Fab lab in Ghana. And I would say that's because I'm a nerd again. My engagement type is more on the lower level. So basically, we build machines together with the local community or the local customers or the local institutions. And we basically invite anyone to the workshop. Maybe even more people are getting inside the workshop along the way. That we also try to do in Bali, by the way. We had a lot of, in the conference, a lot of people joining. And what comes out of it is that the old people that participate, get a lot of inspiration, a lot of knowledge about how the machine works, and now they could, I don't know, build the machine themselves or build their own project with the knowledge that they created. And of course, where do they go? To the Fab Lab. And so this type of engagement basically creates other community leaders and champions, which right now are maybe having other companies or building other machines with the same philosophy, which then fades back in, like a cycle to the open hardware development, but also, of course, into the city. Mm-hmm. And then I can benefit from an improvement that somebody did in Ukraine, in Germany, and vice versa, basically.
Yeah, I mean, it makes so much sense to a FAB community, right? And I think that this idea of collaboration at distance is something that, as the FAB world, we're really quite aware of. But I think it takes another life of its own, almost, when you put in the hardware capacity.
Sure.
And then, on top of that, when you bring in the community capacity. So how do you understand collaboration within the layers that you work in, Jose? And I think, you talked about different types of people who come and engage in the challenge or the awards. What types of stakeholders and how does that collaboration happen?
Yeah, this is amazing, Kate, because I think here is a key point that it's working with local communities. I think that this is something that it's super important in the work we do in Fab City, and the knowledge, how the knowledge is being transferred through local communities, right? So how do we take the knowledge from the Fab Labs, from, let's say, from those four walls outside that, right? So I think this is super important in the sense, how do we involve the local communities? What are their needs? And how can we build skills development in that sense, right? So I think the three layers are actually interconnected because, of course, in the case of, for example, in Costa Rica, it's a Fab Lab. We have the machines, we have the tools, but we need the people, right? We need the knowledge transfer, we need the skills development, and we need to work with the local communities to understand what are their needs at one point.
Wonderful. And so the learning and the prototyping happen interchangeably and happen together. I mean, it's learning by doing, as we do in Fab Labs, but also with the community layer.
Exactly.
That's interesting.
Exactly.
So I have the same question for you, Stefan, and I think in your case it's quite interesting because I have a little bit of background knowledge about how you got involved, in that you actually have coordinated a public-private partnership in order to make this happen and to get your region involved in the Fab City. So maybe you can talk a little bit about that, about why becoming a region was important and how you did that from a governance perspective.
Yes. So first of all, I have to go maybe a step back. It is important to actually think what a bioregion is and what it means. Normally, you're saying that it's about the geography and the biology around to use resources that are grown in the region. But we also have to think about actually the people living there and the networks, institutions that are already in place. And it doesn't make any sense to really look at cities that are close to each other, like in the Bergisch Triangle, and just say, okay, each of them should be like self-sufficient. So each of them gets like a microchip factory or something. This is not sustainable either. You really need to look at how networks are existing, and we saw that in this triangle, the cities are very close to each other, and they have been working with each other for a long time historically. For a while, they even thought about becoming just one city. Well, because they are so close interconnected. And very many institutions are already not working like local in the cities, but like in the region already. So we just took what we already saw and got and worked with these and worked in these cities. But on the other hand, still cities are still separated, also in the head of the people. So it is very important to not just work like locally, think globally, but also think regionally, and think what networks there are, how the culture is in the region, and basically how the institutions then are. And that's what we just went on. We looked for partners. We have in total we are 8 working partners. 5 of them are institutional partners. 3 of them, 1 in each city, are our innovation labs. We are at the moment working on a 4th one at the University of Wuppertal. But that each city and also each of these innovation centers is like still its own entity and also has its own tasks and projects. So we allocated the 3 sectors we're working in and distributed them, 1 for each of these innovation centers. So it's very important, and it is also a bit of a dilemma, of course, that you are trying to work together, but at the same time you need to distribute the tasks that you can still be your own entity. This is very hard, of course. So therefore, a lot of our work is really in the management level and just like a facilitating level, let's say, to bring the partners all together on the different levels actually, and opening up. For example, the maker spaces that we have, the workshops that we're having in the region, they are, at least not all of them, are really part of Fab region on our project, like working with us. We actually need to go with them, go to them, talk with them, and hey, please open up to society. In Germany, we still have this word. It's called Kirchturmdenken, which is like translated saying like everybody's just thinking about their own church tower. Mm-hmm. And we need to open this up and really just like look regionally, look culturally, look bioregionally, and work together there. And because very many maker spaces, let's call them workshops, they are still closed and say like, no, we want to work on our problems, not the regional problems, or we are just open for one specific type of makers. And that's a lot of work, really to convince stakeholders and people on all levels, like really on the ground level, but all the way up also to the regional, to the political level, to get engaged and work together. They speak very different languages, have very different aims, and that's a lot of work. And so I think it was very important that we focus like on the like in the level that is between these two, and got together with different stakeholders, institutions there. So we are also having leverage, that's a word I like, to both sides of the model.
It sounds like, from everything that you're saying, that none of you particularly have the answer on how to do this, which, I mean, isn't that a wonderful space to be in? And that's who we are as a community. This is about creating spaces to experiment and spaces to understand what is the role of the Fab Lab, what is the role of the Fab Lab beyond the doors of the Fab Lab, which is what you so eloquently described.
I think in the end we all like to become irrelevant, that it all works by itself and be also running by itself. I think that's a big goal. So if we had the answer, we wouldn't be necessary anymore, I guess.
Which, could be wonderful, right? We produce everything we consume by 2054, and we go on holidays. I think that would be lovely. I would like, because this is a Fab Labs to Fab Cities to Full Stack panel, I would like to ask the pointy question, which is, what is the role of Fab Labs? What is the role of Fab Labs in each of your layers or each of your interventions? Daniele.
Yeah, well, I think I stepped into a lab. I saw a lot of things that I liked, and that shaped a lot of. I changed the country where I was living. You know, I quit my job and went to work for a public university in Germany. Well, there is a. I mean, the first role I see is for sure inspirational. You know, and it sort of gives you a lot of different perspective from the traditional society, which is already, you know, very much structured in blocks and in things that's hard a bit to step out from. And then I think for sure education and inspiration is one great thing. With our machines, we also hope that, you know, it goes very much outside the doors and maybe in many hobbies to start, or for example, institutions and schools. So for example, one of the first uses of our small laser cutter was to be built together with high school students in Nordrhein-Westfalen in Germany, you know. And I mean, this for sure could bring that kids to the lab later on, or for example, teach the teachers how to use a laser cutter. But behind that, really, we would like to. I mean, our dream is also to, you know, to become the Prusa of laser cutters one day, you know. So like
challenge, okay.
Somebody is listening here. I mean, we would really like to democratize the access to open hardware very much outside the doors of the lab in everyone. I mean, if at the beginning our machines were good for hobby use, nowadays we would like to have them like as a standard lab use, maybe like prototyping, a bit more advanced, or maybe small companies in the cities can get these machines to boost, you know, their production. Imagine like a woodworker that wants to make furniture and doesn't have the money to buy the machine, or wants to learn how does it work, or make some customization to the machine to realize what the local community in that city specifically need, or maybe with that specific design or, you know, type of tradition that they have. And latest, but this is a very long-term dream, I mean, more into the serious, work of production or industries and so on. But this is a very long-term dream of changing this mindset. So we would like really slowly to penetrate everywhere, and we hope that we can, successfully implement, the outcome, the impact of the labs in the world by making machines. So what changes in the world if you can build your own machines in the lab and use it for your business, for your city, for your life, for everything. So that's our long-term dream.
Yeah, great question. What changes in the world, and what can you change in the world, right? Yeah, Jose?
Okay, so from my end, I'm gonna go up, first, personally, I think, for me personally, when I arrived into the first Fab Lab in Barcelona, I felt like I felt like home. I think it's a great place for people, I would say it in Spanish, for us that we are no comprendidos, misplaced somehow. Misfits, exactly. So for me, it was like arriving to this amazing place with people that actually was speaking the same language as I tried to do in society. So that's my personal first answer. And then on a second layer, I would say that it's an amazing place to give opportunities to people that maybe do not have the ways to reach to certain places. So I think it's a great place to create a value, a community, and to give a voice for people to actually empower themselves.
Stefan?
I don't know much to actually add to this. I see the same. They are places of empowerment. I like this word, empowerment, actually, really. And of community and a place of belonging. I think it's very important. There are just too many things out there at the moment in society that just distract students, distract people from becoming, to be empowered and to have a feeling of, yes, I can do something, of this maker's spirit. And I think they need to foster the spirit, build up communities that catch each other up and really give competencies to be able to do something for society and for themselves. Yes.
Great. I mean, I think that's a wonderful note to leave this on. We don't have that much time left, but I do hope that this approach through the full stack can be empowering, can be inspiring, and I hope that the case studies that you've seen today pique your interest. If they do, come and see us. Come and see our New City Pledge this afternoon. We have 45 seconds. Daniela told me this morning somebody made a coin on the stage and threw it into the crowd. He would like to give away this book, but I'm not sure that's the best way to go about this. So I think the best way to go about this is we will exit the stage. Daniela will hold the book. First person to come to see Daniela to get the book gets the book. How's this sound? I think this is a safer version, especially on this spinning stage. But thank you so much. Thank you to all of our speakers. Thank you to our cities. And we really appreciate the opportunity to bring the work we're doing here with Fab City Foundation, Fab City Global Initiative to the main stage here at FAB25. It's been our absolute pleasure to be involved. So thank you very much.
And thank you.
Thank you, Guy. Thank you, Kate, for hosting this panel. It was wonderful. And as for you guys, this is the end of the conference part, but the day 6 is far from over. You've still got a full afternoon of workshops ahead with 3 packed pavilions full of activities, making, and inspiration. So please make sure to have your live voice app ready, so installed and downloaded on your phones for the workshops, and bring your headphones with you. And tonight we'll celebrate this new Prague chapter of FAB25 with a rooftop party above the Křižík pavilions, and there will be a great live performance by Eddie Funk called Dear Quantum that turns quantum science into sounds, visuals, and emotions. And now it's lunchtime. You can pick up your lunches at the cafe and bistro, and for me, this is where I say goodbye as your host. But I'll still be around for the rest of FAB25 as one of you, as a participant. Looking forward to it very much. But yeah, thank you for having me. It's been a blast. Enjoy the rest of FAB25. Bye, guys. Thank you.